Okay, teams. I think with this experience, you can see the difference between the theory and the practice, the experimental, right? The first place then is for the National University. Then we have Univalle, the second, and for the third we have WIS. So, congratulations. So we are going to start with the, excuse me? Yeah, so please the captain can come here and choose the place they want to start. The order, yeah.
Which team you want to be? Sorry. Yes.
The order. Me toca estar aquí. So, UN second. Okay. First for Valle. And third. Team A then. And National University is choosing. Yeah, you have time to choose. You want to be B or C? This is the strategy they want to. B. So you want to be B. And then WIS is going to be C. So this is important to know for the people in the streaming too. So they have chosen in which place they want to start. So Univalle is going to start the first round, this first round here, as the reporter, Univalle, and National University from Bogota is going to start as opponent. The opponent will have to propose. No, he's going. No, we have already chosen that yesterday. So Univalle is going to start as the reporter. Yeah. How long do we have for that?
No, wait.
Miguel.
So, first, before we start with all this, we want to introduce you the members of the jury. We didn't do it earlier because we're now transmitting live through Facebook of Parque Explora. Sí. Tell all your family members or your friends who are not here that want to see the fight to connect to Facebook through Parque Explora's account, and so they can enjoy as well as we are enjoying right now. Juries, before we start, we want you to introduce yourselves to the public, to the people. Please, we're going to pass you the microphone. Just say your name and say the university you come from, so we can give the teams a little bit of time to organize themselves and we get to know you a little bit better. Please stand up so you get caught at camera.
Good afternoon. My name is Juan Carlos Vázquez. I am physicist from University of Antioquia, and I am teacher in the Instituto Tecnológico Metropolitano.
Welcome.
Medellín.
Welcome.
Woo!
I'm Johnny Jaramillo. I'm postdoc at CERN, but I used to be a professor in the Universidad de Antioquia.
Woo!
Okay. I am José David Ruiz. I am professor at the University of Antioquia, from which I am physicist too.
Woo!
Okay. Oscar Antonio Restrepo from the University of Antioquia.
Nice.
I'm Camilo Quijano, physics engineer from the National University Medellín branch. and I'm a professor at the Politécnico Colombiano.
Nice.
I'm Carlos Palacio, physicist from University of Antioquia, but I'm working now in Universidad Antonio Nariño.
I am Juliana Restrepo, also from Universidad Antioquia, and now I work at Parque Explora.
I am Alejandra Valencia. I work at Universidad de los Andes in experimental quantum optics, counting photons all day.
Wow.
Volodymyr Akimov, University of Medellin.
Hi, I'm Camilo Espejo, physicist from National University of Colombia, currently teaching at Universidad del Norte.
Nice. So for all those who are watching us right now live, what we have just done is that yesterday we were at the semifinals. These three teams who are now in the finals were competing exactly the same way they are competing today. So the physics fight consists on 3 rounds of discussing problems. The problems have already been decided. They're going to discuss 3 problems of the list of the IPT's list of problems that they're going to solve. Those are going to be jumping beans, cumulative cannon, and planetary clock. We're going to start with the first round. Univalle is going to report on planetary clock, right? No? Wait. Cumulative cannon, sorry. So planetary clock is going to be presented by Universidad Nacional, and then the jumping beans is going to be presented by WIS, right? So there's going to be 3 roles: the reporter, the opponent, and the reviewer. The reporter presents the solution of the problem they have given to it. They have 12 minutes to do so. So in the semifinals, they only had 10 minutes. Now they're going to have 12 minutes to do so. The opponent then is going to ask them questions and oppose that solution, not to actually fight with them, but to construct a better solution to the problem that the reporter has presented. And the reviewer is going to be moderating the fight, as in trying to make them find a common solution or a better solution for it. The juries have the rules, they know what's happening, and they're going to be grading at the end. I only have one thing to ask the competitors and the juries, is that in the moment you are doing questions, they have to be technical questions. There's no use to make somebody look bad with the questions you do. They only have to be questions such as, I don't know, what are the units of that axis? Or did you take this into account? It's not like, please explain how would you do that. If they haven't explained it, they haven't done it, it doesn't make sense to ask them to think something they haven't prepared. It just makes sense to ask something they maybe didn't present, but that you know that they did, and you want to know exactly how they did it. That goes for the competitors and the juries in the moment they ask. At the end, after the juries give the grades, they're going to have some minutes to comment on those solutions or in that discussion. So you're going to be able to say, hey, guys, this is a physics competition. Why didn't you take this into account? You should have, right? But only after giving the grades, so you don't bias the other juries before giving the grades, okay? Are you guys ready? Nice. Let's start. Univalle. Yes. You now have 5 minutes to prepare your presentation. Juries, during these times of preparation, we ask you to take the time. Just to read anything, and if you have any questions, ask us during these times of preparation.
La luz no deja ver. Sí. No entiendo. Who is going to continue? Just to tell. No. The presentation. Ah, it's there. We are asking. Okay, good. Who is going to continue presenting? The discussion. Yes. Just for you. Let's go.
Yes.
Okay, I'm going to take advantage of this minute that they still have. We want to remember everybody, all the members of the teams and the jury, that during the physics fight, which is the whole thing, the whole 3 problems, each member of the team is allowed to take floor only once, right? So for example, if Felipe is going to be presenting right now, he's not allowed to take the floor on another problem later. And for the reporter's presentation, each team is allowed to have 2 people on the floor only during the presentation, but not during the discussion. So during the presentation, we're going to have 2 people from them presenting, but only Felipe Reyes doing the discussion. That's right? Okay.
Okay, Felipe, so you're going to have your time from now? Now.
All right, good morning, everybody, and welcome to the first round. My name is Felipe Reyes, and together with my friend Juan Manuel Escarpeta, are representing Team Univalle, and we are going to be talking right now about the problem number 1, cumulative canon. So without further ado, let's go. A really brief recap of the problem that we're going to be discussing right now. We have a ping pong ball resting on the surface of a water cup. The cup and ball system is going to be dropped, and when everything falls and receives the impact of the ground, the ping pong ball will bounce up to much greater heights than it was originally at. What are we going to do with this? We're going to analyze this phenomena. We're going to look into the physics of it. We're going to see how high the ball jumps, why it jumps, and we're going to be answering what is the fraction of the energy that is transferred to the ball during all of this process. So the model that we're going to be using for this is we're actually going to be focusing on the shape, on the way the water surface changes shape during all of this process. So we're going to be looking at the water surface as a medium through which waves propagate. So to model this, we're going to be using the world famous wave equation over there. In this case, z is representing the height measured relative to the equilibrium position of the water. All right, so we are only going to be interested in symmetrical hits. Why is this? If you look at a plastic cup, if you look at the bottom of a plastic cup, you will see that it actually has a little ridge close to the edge. So this means that the impact is actually going to be distributed along this circle. This is going to end up being a symmetrical hit. And that is why we're only going to be interested in symmetrical solutions to the wave equation. So to solve this, we actually do some polar coordinates, perform a bit of variable separation, and with that, we can get our free motion solution, which is what you see up there. It is in terms of the 0th Bessel function of the first kind. And additionally to that, we have to apply a constraint. What is the constraint? Well, we can't create water, we cannot destroy water, water must be conserved. Therefore, how do we show this mathematically? Well, it's pretty simple. We just integrate over our solution to make sure that the volume remains constant through this entire process. And after doing that, we can find an expression for kappa in terms of the zeros of not the 0th Bessel function, but the first Bessel function. With that, we can finally have our free motion solution, which is what you see down here. It's in terms of an infinite series of Bessel functions, but it will converge to our solution. And with that being said, we're not really interested in the free motion solution. Why is this? Well, it's because the cup is falling to the ground. It's going to be receiving an impact, an impulse, very localized in time, very localized in space. So what we're actually interested in is the forced motion solution of this equation. And as you can see, this means that we really have to solve this equation right here, which is the non-homogeneous version of the wave equation. What's the solution, you may ask? Pretty simple. It's the Green's function of this differential operator. So this is what we're going to be calculating right now. We expand our Green's function, g, in terms of the eigenfunctions of our differential operator. Which are those? It's fine. We just figure them out in the free motion solution. We know, for example, that for the radial part, the eigenfunctions of this operator are the Bessel functions of the first kind, the 0th Bessel function, in fact. And with that, we just plug in that expression, that eigenfunction expansion, back into our non-homogeneous equation. And after a bit of algebra, a little bit of differentiating, we have finally our forced motion solution, which is the Green's function for this operator, which is this one at the bottom that you can see right there. And over there, you can see the functional form of those m sub n coefficients. So finally, we have our solution for the Green's function. What does this allows us to do? It allows us to see how the water surface changes when it gets hit. And you can see it has those peaks near the center. You know what else is at the center? The ping pong ball. So it is this change in shape that is going to be propelling that ball to the great heights that we see when we perform the experiments. So if we can go back to the presentation, what we must do is we must track the center point of the membrane, the center point of the surface as it moves through time, which is that red line over there. So it's pretty clear that the ball is going to come out of the surface. It's going to start flying up at some point in the upwards trajectory of the water surface. But we cannot be sure where that is. Why? It's because the point at which the ball starts flying depends on the point at which the normal force between the water surface and the ball becomes 0. That's a pretty difficult thing to model. So we cut around this corner by just taking the average velocity, which is the slope of that line you see right there, as the surface moves up. With that, we can just scale that slope up by the magnitude of the impact, which is that F you see over there. It's in terms of the change of momentum over the time that collision takes place. So we model it with that equation you can see over there at your further right. But this is not an elastic equation. It's very inelastic. There's going to be energy losses due to the creation of the ripples, creation of the waves, the deformation of the cup. So we add that epsilon you see right there, which is the inelastic coefficient, which will be very important in a couple of slides. Additionally to that, we can calculate the exit velocity by, of course, scaling up the slope we found in the previous slide and subtracting that Q coefficient. That we call an interaction coefficient. And inside that coefficient, you have information regarding the interaction with the interaction of the water surface and the ball. That's a pretty difficult thing to model, so at first, we're just gonna be using it as a fitting parameter. With that in mind, once the ball leaves the water surface, it's flying through the air. It's a big effect that's gonna be taking place is air friction. Why is that? Because the air friction that a body suffers while it moves through the air, it's actually going to be dependent on the ratio of the weight of the ball, in this case, over the drag coefficient. So we take a drag coefficient constant, which is that 0.445 you see up there. That drag coefficient usually depends, it has a functional dependence on the Reynolds number, but for the velocities that we're interested, it's a very good approximation to taking constant, as you can see in that graph there. The dotted line takes into account the functional change, but if we take a constant, we get the solid line, which is barely any different, so it's perfectly okay for us to take the constant coefficient. Now, here we have Newton's equation. We just solved the equation of motion for the velocity, and integrating that, we have the position of the ball as it moves through the air. So in this graph, we can really quickly see how the purple line over there is the trajectory without drag. It reaches a very big height. Actually, it reaches more than twice the height it reaches when we take into account drag. So it's very important that we take into account this phenomena, and this is how we're going to be moving forward. So we performed the experiments. We filled up a lot of water cups with controlled amounts of water, and we started dropping them from control heights. And with a video tracking application, we managed to figure out the height that the ball reached. This we repeated many times to have something that we could compare our theoretical prediction with. So right here you can see this line over here is our prediction, and our data fits very well. In fact, when we fit our free parameters to it, we can have epsilon on Q with 2 sigma confidence down to less than 1 part in 10, which makes us very confident that this works. So regarding energy loss, we just take that epsilon coefficient we just saw, and we can calculate actually that on collision about 20% of the energy is transferred to the ball. After that, there's an additional energy loss due to the air friction, but that depends on the initial velocity, and you can see how that dependence looks on the graph over there. Now, we have to talk about that Q coefficient that I was telling you about, which is quite important, and my friend Juan Manuel Escarpeta is going to take it away from here.
Okay, thank you. Well, in order to improve our model, as my friend said, the Q coefficient, we have to include another model to explain the interaction with the ball and the surface of water. So this is what we're going to present. Well, we choose this equation that describes this interaction, and we get this, f sub p. So this equation it's in terms of the buoyancy of the ball, the viscosity, and the added inertia, because we are working in a non-inertial frame. So these functions that you're looking here are presented there. So the final equation of motion of the ball, we include the weight of the ball, we include the surface tension of the ball, and we also have a geometric condition for the solution. We also have an expansion of the height of the ball and the angle beta of contact with the ball with the water. So our perspective is to get a final complete description of the phenomena. We have to merge the model, and the solution is perfectly complete. As a final remarks, we see in the model that we get good fit parameters in the theoretical model and the experiments. We get also a numerical solution and animation in order to to visualize the phenomena, and also we, of course, we solve the question we get, and the kinetic energy fraction we can transfer is about 0.2 of the transfer to the ball. I think that's all. Thank you.
Okay, so now the members of the opponent team are allowed 2 minutes to ask technical questions about the presentation. Let me give you the microphone.
Okay. Good morning, afternoon, audience. Good afternoon, audience. So, my first question is, how many measures did you do?
Of course. Can we show the graph really quick where the experimental
No,
result?
how many?
How
The
many?
number, quickly.
Oh, we did a bunch, so I was just wanted to show you the number of points. I don't have exactly the number. We did several tries for many heights. We did
An approximation of the number of the measures?
about 40 tries.
For 40?
Yes.
Okay. My next question is about the symmetry. Can I
Symmetry.
see the slide 5, please?
Yes.
No, sorry, 7 could be slow.
Slide 7, please.
The final, the close answer to the question of the problem, please. The final, I mean.
The Green's function?
No, the hike in terms of the more important parameters.
Sure. Can we go a little bit further? Okay. Yeah. Over there, what we have is a function, a series of functions that takes us from initial height to the impact velocity to the exit velocity to the maximum height. We don't have a clear function. There's definitely a functional relationship that we know, but a lot of this is done computationally, so there's no closed form.
But you can clarify me, please, what are the main parameters that do you consider more important to this experiment? I mean, okay.
Absolutely. The mass of the water, the radius of the cup, the depth of the water, and the initial height that you're dropping it from.
And your approximation, please?
Which one?
Your approximations. I mean,
Of
what do you...
Can you point me to the slide you want to see?
That's time. Sorry. Now the opponent has 3 minutes to prepare the preparation they're gonna give. Okay. Meanwhile, they prepared the presentation. I just want to clarify what they're doing right now. So the opponent right now is trying to prepare some presentation about the things that the reporter reported, right? So they're making up a presentation. So they give like the highlights of the presentation the reporter did, or the things they consider it could have done better, or the facts that they think that should have been done in order to solve the problem better, or to discuss the problem further in the future.
Now you have 5 minutes for your presentation. The opponent.
Good afternoon. My name is Alejandra Larcom from National University. So, in first, I want to say that the model presented by the last group is a very good model. A very good theoretical framework was development. Okay, I want to. So, cumulative canon. So, what are the strengths of the reported? They have a very good presentation. They have an analytical solution of the problem. They abort it with waves transfers to the ping pong. Takes air friction into account. Data feed theoretical results. I think that we could say a lot of very good equations. However, I think that there are many things some things to improve, and there is about the experimental results. I would like to see more experimental results and statistics. I think that they explain the phenomena in terms of a wave, a propagation of a wave, but the more improvement that they could take into account is the pressure in the phenomena. I mean, it implies an area of contact, and it isn't an instantant. I mean, it isn't instantant, and there are an area that they could take into account. Another thing that I want to say is that they could show us about experimental results compared with a theoretical framework. I mean, the more important thing that we need to have into account when we do or resolve an experiment is develop a theoretical framework, but two, that it corresponds with the results that we develop in reality. So I would like to see the prediction of the height with the experimental results. I would like to see too the limit cases. I mean, where your theoretical explanation take a good. I mean, where is the boundary of your explanation? And another point is that I would like that the other group could focus on a simpler physical explanation. I mean, goes in a way or the physical meaning more than the equational way. The equations are a very good tool that could explain us about the physicists of the problem, but what are the most important principles that we take into account in this problem? So I can finally hear and hear you, please. Thank you.
Okay, so now the reporter and the opponent have 5 minutes to discuss about what they both have presented.
All right, well, that being the case, one of the things the opponent was making a bit of emphasis in was our experimental results. And I do agree with you, experimental results are great. However, we have a good few of them, and even with those, they were enough for us to narrow down our free parameters down to a very good precision. We had less than 0.1 uncertainty with 2 sigma confidence. So sure, we can take more experimental data, but that's only going to narrow down our parameters even more, and it's going to make our model even more solid.
Okay, so I want to see the experimental result, please. I don't know.
Please go to that slide. There you go.
Okay, where are the error of these measurements? I mean, what is the the error, yes, the bar error.
Actually, we used a video tracking application to measure the height. So if you look really closely, there are error bars, but they're really small. They're about the size of the dot.
Yes, but it is necessary because we need to know how precise is your experiment. I mean, you don't have just the error of the program that you measure.
Oh, but the error of the program
please,
is fine.
Hear me, please.
Sure.
But also the angle, for example, the camera, with respect with the wall.
Yes, we made very sure that we were being parallel to the wall. That's not an issue right here.
Okay, don't worry. Can I see, please, the theoretical framework? I mean...
Please. Which slide would you like to focus on?
I would like where can I say the limit cases. I mean, when I let fall the cup, yes, since 0 height, what is the result of your experiments? It reproduces just the ping pong fall?
I mean, the great thing about this model is that the limit cases are very much included. In fact, one of the limits we could take is dropping it from a really, really high altitude. But if we do this, the cup is going to break and we're not going to be seeing the phenomena. So that limit is way beyond the scope of this model. This model works very well for all the heights that are going to be showing this phenomena.
Sorry, could you explain me better that? I mean, simpler?
Yes, of course. If you drop the cup from too high, it's going to hit the floor with way too much force, and the plastic cup might break. Yes, you're definitely not going to be seeing the ping pong ball bounce to the heights that we see and to the heights that we're really interested in. So if the cup breaks, that's not really the phenomena we're interested in.
But if you let fall it of a very, very small hike, yes, what is your answer for the problem?
Actually, there is, if you drop it from too low, it just won't jump. And that has to do with the Q coefficient that I was showing. There's some interaction that we are looking into, as we showed at the end of the presentation, that is slowing down the exit velocity. All right? So for too low of a height, you won't see the ping pong ball jump. But eventually, it will start rising up.
Okay. And now, where is the explanation of the cup? I mean, the material of the cup. Because, like you mentioned before, if they broke, it is very important limit. So where is in your theory?
I disagree. It's not a very important limit because if it breaks, you're not going to be seeing the cumulative canon that is what we're interested in. If it breaks, the ping pong ball will just not bounce to the heights that we need it to. If it breaks, this is not the phenomena we're interested in. So we're not really concerned with that limit.
But it is very important because if the elastic properties of the glass is in here, in the cup.
It is, and we include the inelasticity of the collision, which has something to do with the material of the cup in that epsilon coefficient right there.
Okay, and what happens if the cup is of metal?
It's of metal? Sure. The inelasticity coefficient is going to change because it's probably going to be a more elastic collision, more energy is going to be conserved, and you give me the cup, and we make some tests, we fit our model, and we'll have an easy way to make predictions.
Could you explain me more about your inelastic collision? I mean, in what way you are talking about it?
Okay, you may talk about that a little bit later. Now we have 2 minutes from the reviewers team to make questions both to the reporter and to the opponent. There you go.
Okay, to the reporter, I want to one technical question. What was the resolution of the camera that you made to the video processing?
We used an iPhone, so they're one of the more high-resolution cameras that are commercially available.
The frames per second.
The frames, 60 frames per second.
Okay. And the dimensions of the ball, the ping pong ball?
Radius 2 centimeters.
Weight?
Weight 2 grams, 2.6 grams actually.
And the dimension of the glass?
4 centimeter radius, and the height of the glass doesn't matter so much as the depth of the water.
the program of the simulation, of the membrane simulation.
Which one? Oh, the surface.
Yes.
Yeah, we ran a code in Python that we made ourselves, and then we just graphed it and made a GIF.
Okay.
What is the relation between the drop height and the initial height? And the final height, sorry.
I can show you the graph if that's what you mean.
You put, please.
Can we go to the graph? Next. There we go.
How do you calculate the sigma and the confidence?
We used a stochastic fitting method that we developed ourselves. One of our colleagues is his thesis work.
And how many points do you take into account to do that?
For the fitting? Oh, it's actually a stochastic method, and we run about 200 Markov chains, each one taking about 10 million calculations.
Do you take into account the viscosity, or you try other liquids in your experimental setup or in the theoretical?
Okay, so that's it for the time of the questions from the reviewer. Now they have exactly 1 minute to prepare the presentation. They're gonna do to review what has happened until now. During this minute, I would like to say that maybe you have noticed that the teams interact with the reporter and the opponent all the time, while they are not doing a presentation, but they're in a discussion. They are allowed to have comments or things to say in written form, so they can interact with them and help them a little bit, but only them can talk and be at the floor during the discussion. So right now, the reviewers has 3 minutes to give them speech about what has happened till now.
Okay, good afternoon. My name is Steven Rico, and I'm going to be the review of this problem, the community canyon problem. This problem asks for two main points, right? The maximum height that the people may reach, and the fraction of energy. So I'm going to start with the review. The reporter, okay, they focus mainly in the theoretical part of the solution that is actually a really nice one, yeah, and I think really complete, but a little too heavy, as the opponent mentioned, right? They talk about symmetrical heat. I mean, you focus on the symmetrical heat, and I want to talk this later because it concerns me a little bit. And, well, it was actually a complete solution from the Bessel functions to the green functions. Well, they show a confusing video because we actually couldn't see what happened to the ball in this part because the bar of the reproducer were covering. And you talk about the energy of the ball, that it was 20%, yeah, but I didn't get clear if this was by the model or by your experimental data. And you talk also finally about the forces, including the ball. The opponent make a good technical questions about the relevant parameters, the repetition of the experiment that actually matters a lot in this case, and the assumptions that you made to make your model, to your theoretical model. She asked for the conceptual explanation. She pointed out that you needed more that you need to show the experiment and the statistics of this problem. She talked about that she wanted to discuss about the boundary condition, and she asked for, in this general discussion, to talk about a simpler explanation of the model. So I think we can focus on this. They talk about the statistic in the discussion when the reporter actually didn't show a standard deviation, and the experiment was a little confused. They didn't agree in more sources of error. And, well, when they talk about the limited cases, the reporter said that the upper limit can be achieved because of the damage of the glass, but it was a little misunderstanding then. Okay. So, the strengths of the discussion, but that's what there was actually a real clarification of the limit cases thanks to the opponent. There was very dynamic discussions. In the weaknesses, I think the reporter had a little hard defense, and there was lack of number. So I'm going to pass to the discussion part. So, well, I invite to my partners here. Thank you. If you wanted to talk, please raise your hand. I'm giving you the word. And I think, can you come closer, please? Of course. I'm going just to use one mic, so I'm going to give you the word so you can talk. But just using this microphone. Yeah?
Okay.
Okay. So you ask for the discussion to talk about the simpler model that can explain this, and this is actually an important thing, yeah? So I'm going to start this. You model your theoretical explanation as a membrane, yeah? Do you think that this is accurate since there is not just a membrane, but there's a volume of water under it? I mean, think, for example, in a drum. Yeah, you hit a drum and it's a membrane. But if you put the drum, well, the plane under the water, the oscillation is going to change due to the volume of water under it. Do you think that the modulation as a membrane is accurate?
I think that is very complex because it phenomena could be explained easier and better with analysis of pressure. And I think that the reviewer don't mention a close answer in which can predict the reporter. Yes, the reporter don't mention how can I describe or predict the height with the most important parameters of the problem.
Because we see that there wasn't, for example, in the experimental, there were a lot of variation of the parameters, right?
Yes, and I think that I would like to see a table with the experimental results to clarify this point. I mean, they say that it's very approximately, but don't show what is the result.
Thank you. Yeah, I think that the experimental lack is a hard problem here, but I'm going to ask you about what do you think that could make simpler your model, your modulation, your theory modulation?
Yes, just because the equations are difficult, it doesn't mean, I'm trying to be quick, but you took a little bit of time. So just because the equations are difficult doesn't mean that the physics behind it is complicated. Nobody here, I think, wants to deny that waves propagate through water, and that is exactly the phenomenon we're looking into. So just because the equations are hard doesn't mean that there's no physics involved.
I think you didn't answer my question.
Are you saying that there are not simpler models that can predict this phenomena?
I mean, whether our model is difficult or not, it actually predicts the results very well. So a simpler model might not be true. Our model seems to fit the data very well, as I showed, so there's no need to simplify it. There's no need to make it more difficult. It's working.
Okay. I said that I was concerned about you said that you only focus on symmetrical hits, right? But yesterday we saw that in some groups they actually present the experimental video when the hit actually perpendicular, there was in a formation of the water column. Do you think that this inclination, well, we see that effect, but do you see that this assumption is accurate in the model?
The inclination, I mean, the symmetry respect the axis, the cylinder?
The symmetry of the hitting, I mean.
Okay, I think that it is experimental. I think that the answer to this question is an experimental issue because I want to say, how do you guarantee this symmetry?
That's a good question.
Sure, I talked about how the cup has a rim around the bottom, close to the edge. So it's definitely, the hit is always going to be close to the edge. All right, we can have asymmetrical hits, but you're asking me not to complicate my model. Of course, I could add an angle dependence, and we can find the Green's function for that. But there we go.
Okay, so now
we're going to enter to the team.
Exactly. Any member of the team can take the floor or ask questions or give any explanation from the public.
Okay, that team, please.
One question for the opponent. What do you think are the most relevant parameters in order to obtain the maximum height?
For me?
Yes. For you.
Okay, I think that the more important parameters are the elastic property of the glasses because it gives a limit, the masses of the water, the mass of the ping pong, the area of contact because there are a pressure, the water is an incompressible fluid, and in this way there are a pressure transferred. A very important issue in this problem is the area in contact with the water and with the ping pong. Of course, the initial hike of the lanzamiento.
Okay. Okay, thank you. Do you think that those are the relevant parameters, or do you want to add one?
I actually think the relevant parameters is actually the mass of the water because the momentum transfer is going to eventually depend on this. We can include the contact surface area of the ball with the water, and we do in the Q coefficient. It's not very well understood, but that's what we're trying to do with the complementary model we showed at the end.
Okay, I'm going to make a stop, so please the team partners could just move a little bit, please, because can you go to your place or raise your hand so I can give you the word if you wanted to talk.
They're actually allowed to take the floor during this session. Yes.
Oh, okay, doesn't have a problem. So there's another questions. I'm going to give it to you.
Okay, again, I would like to know how your model predict that the cup breaks or that something related to the quantity of mass or the quantity of height could affect the cup in such a way.
Of the break of the glass with the epsilon parameter, that is the inelastic parameter, and we can include two functional dependent with the height, initial height in this parameter and fit it. So this model can reproduce all these phenomena.
I just want to add a really quick thing to it. As I said before, we're not interested of it when the cup breaks. We're interested in the cumulative canon phenomena. When the cup breaks, we're not going to be observing this, so this is beyond the scope that we want to study.
Actually, I agree with the opponent part because I think that this will settle a limit, a boundary condition of the model. I'm going to give the word there. So.
A question for both of you. How do you improve the experimental setup in order to obtain the maximum energy transformation? That is the second question. How do you improve the experimental setup in order to obtain that?
Sure, you change the cup for one that's more elastic. And as with the cups we tried with the same cup or the same type of cup many times, and we found that the collision loses about 80% of the energy. Just find a more efficient cup, a more elastic cup, and there you go.
Do you think that just changing the cup will make more efficient the experimental setup?
A way to make more efficient the experimental setup, yes. Okay, I think that change the cup. I think that it is very important, the issue. But I think that the more important issue that the video exemplified, but was very clarified, is that the movement of the glass, because it guarantees the symmetry axis. So the reporter don't mention that, and that is the form that you guarantee that the cup fall down, guarantee that the cup fall down exactly or approximately better in that way.
Okay, yeah.
For example, you can improve. You can improve your experimental setup, maybe changing the area of the cup, because it's very important for the transfer of pressure. Yeah. So for me, it would be better that you can improve your model or your experimental results, changing the area of the cup and do all the analysis.
Well, now that we are talking about the transformation.
Really quick?
Yeah, sure.
Thank you. I agree, and I really do appreciate your suggestion with more experimental results. Of course, we can add them, and that's only going to narrow down and make our model even more. It's going to add to our confidence of our model because it's going to narrow down our parameters. But of course, we should have an effort, and I believe with your suggestion, we can achieve a much, much better model, even though we already have the theoretical basis pretty much set.
Oh, I think that we get run out of time.
Yes, so teams, please go back to the public. Right now, only the reporter stays at the floor, and they have 1 minute to conclude remarks about what just happened during this discussion.
All right, the time's running. Well, I think it's a very interesting phenomenon. It's something that we can do, everybody can do at home. Just get a cup, get some water, a ping pong ball, and watch this phenomenon. But it's very interesting how just a simple physical system can have, as both of my fellow teams said, a complicated solution. That doesn't mean the physics is not there. That just means that we need to work a little bit harder to get it. And I think that's something we should strive for. And thankfully, with this discussion, we found some key points that we can work on. We can definitely find some more experimental points, and I would love to work jointly with the Universidad Nacional's team in the experimental department. And of course, we can get more experimental points, narrow down our parameters, and be even more confident in our model. So with that being said, I think this was a fantastic discussion, and I hope both teams, my own team, and the members of the jury, and the general audience are more informed about this problem. Thank you.
Okay, awesome. So I invite the reviewer and the opponent to the floor, because now right now we have 6 minutes for the jury to make punctual questions, to make technical questions about something that they may have not understood, or something they want to understand a little bit better of what has been done, and there's 6 minutes for that.
What do you think about the role of the roughness of the ball? Do you think it's an important parameter in the final results or not?
Yes, it does have an impactful role in a couple of places. One of those is when the ball is already flying, because in the graph I showed of the dependence of the drag coefficient, it's different for a smooth ball and for a rough ball. But for the regimes we're interested, it's not too big of a difference, but we could look into it. And also the ball-water interaction could be affected by that. So we would have to look into modifying our derivation from the unsteady Bernoulli equation that we showed at the end. But yes, we could look into that.
The juries, please make sure to tell which one of them you're asking the question to.
Okay, thank you. I'm asking to the reporter.
Yes.
Could you show me, please, the slide about the water and the ball interaction?
Sure. Please go towards the end. We have a few of them. This one is the first one.
This one, which is the parameter that you will associate with hydrophobic or not hydrophobic material?
In this case, we're assuming that the ball is completely hydrophobic, and that has to do with the other juryman's question regarding the roughness of the ball. If we change the characteristics of the material, of course, we should change this equation, but this is for a non-porous hydrophobic ball.
And did you really did the numerical simulation of this part of these equations, or only
we did solve these equations. Can we show the annex? Do we have it there? We did solve it, just integrating with Runge-Kutta method. Yes, and you can see how there's a dependency. I hope we have it. However, what we found is that the velocity you could predict with this is nowhere close to what we actually observed, and that just tells us that there's way more than just the interaction, and of course it has to do with the wave equation that we presented at the beginning. We don't have it? We don't have it. I'm sorry.
Okay. I have one question, and I would like to have an answer from the opponent and the reviewer. What do you think, apart from the number of data that the team has taken, what do you think about the model and the data that they have fit, they really have shown that the model predicts the data or not, and why?
I think that I want to see more in detail the simulation and the theoretical framework because in the slides don't there a close answer of the problem. So if I give one measure, you can answer if or what is the height that they could go. So I am not sure about the method because there are many variables, for example, the pressure and the area that determines this process and they don't take it into account. So I think that I would like to know what is the limit of this explanation to answer this because I can see or I can say that it model works if I don't have that limit. I mean, I can see the answer when the height is 0 or when the height is 1 kilometer. Or for example, if I put 1 kilogram of water, I can see the answer. So I want to see the limit.
For me, the theoretical, I mean, my concern is more of the experimental part because I don't think it actually will fit. Because you said, well, the reporter said that they try 40 times the experiment, but actually they didn't clarify which are the parameters that they change and if there was like a control, one or a no control. For example, we just vary the mass and these are the results, or we change the glass, the mass of the water, the height, yeah? I don't know if I made myself understand. Thank you.
This question goes to the reporter. I would like to go to your slide where you have your experimental data points.
Please.
You said that your error bars are within the data point, right?
Yes.
Could you explain me a little bit better that curve? It's not really clear to me. You
Sure.
said it fits.
Of course.
Thank you.
With every single step of the model, what we're actually having is a function that, you know, as the opponent said, it's not closed form, but a lot of physics problems are not closed form. We had a function, you give it initial height, you find the impact velocity, you find the exit velocity, and with that you can find the final height. And that is what this graph is showing. We give it an initial height, which is our independent variable in the x-axis, and the line tells us what is the predicted height that the ball will reach. That is the dashed blue line over there, and the points are the ones we measured, throwing the cup from different heights, and they're lying close to the curve.
Okay, awesome. The teams may now go to your seats. There's 1 minute for the jury to decide the marks they're gonna give to each, the reporter, the opponent, and the reviewer. So just to clarify to the public who's watching right now, this is a competition. The juries are deciding marks between 1 to 10, and there's gonna be like an average of those marks that at the end it's going to count to know which is going to be the winner of the competition, and therefore who is going to represent us internationally in Poland in 2020.
Okay, it's time so for the jury to decide, please, your marks for the reporter. And that is 7, 7, 8, 7, 7, 9, 8, 9, 8, 8. Okay, thank you very much. Now please your marks for the opponent. And that is 8, 7, 9, 765 7777. Okay, thank you. And now for the reviewer. Please, your mark for the reviewer, which are 8787678876. Thank you very much to the jury. And this is now the time for the jury, if they want to give some comments to the people who are here in any one of the three roles. So please, if you have any comment, Camilo.
Okay, I would like to comment about the work done by the reporter. Perhaps it's interesting to see whether the numerical solution of the wave equation was compared to the video of the movement of the water, the surface of the water, because I think that it could give us some clues about the accuracy of the numerical model and the wave equation that they have done.
Okay, yep. Any other comment? No?
There's no need to.
Maybe
but
Juliana, who wanted to make a question before, didn't have time, but now
I don't know if it's a comment or a question for the opponent, because you were asking for simpler models, saying that these were very complicated models, but you have models at different stages, like one is for the wave, one is for the impact, etc. So do you have a simpler model that describes the data?
I think this is not the moment. Maybe we can, like, through coffee, you can discuss it, and that's the point of the physics fight, right? But right now it's just comments from the jury, which a question is also a comment.
I have.
Yes,
thank you.
Very small comment actually for the reporter. I would like to hear from this type of presentation a quick and insightful statement about the physics. So I think you have concentrated a little bit too much on the equations and so on, but it would have been nice actually to understand, for example, in a very quick phrase, why the ball goes to a higher height when dropped in this form than without the cup, for example.
Okay, thank you very much. So if there are no more comments, so we are going to, this is the end of the first round. And so we have maybe 5 minutes rest, and then we come back. And because after the next time, after the next round, we are going to have some little food, yeah? Okay, thanks to the jury, thanks to everybody. Lo que se decía. Round. Uh, so from now we ask Universidad Nacional, please come here to prepare the report. From now, 5 minutes. National University. Okay, the reporter is ready. Are you ready? The microphone. So the reporter is going to be Nicolas Gomez.
Good afternoon. So I am Nicolas Gomez. I am going.
Give me a minute. I give you the signal right now.
Okay. And I am going to report planetary clock, and I am representing Universidad Nacional de Colombia. So here we have the content, the problem statement, the setup and design of our clock, the theory behind it, the error and instability, the most important things in a clock, the calibration for different planets, which was one of the questions from the IPT, and some references at the end. So the problem statement is about proposing, that's an important word, proposing, the most accurate clock that measures time with a temporal resolution of 1 minute, or it could be less. The clock should, or the design of the clock should calibration for the clock to work on another planet, and we are asked for with what certainty will your clock show the correct time after 1 year. So, let's start with the setup and design. What do we need? What we are going to use? We are going to use a Sagnac-like interferometer, which is a device like this. It works with a source, a light source, which emits a beam. The beam is split in 2 parts, and these parts are going to go in different or opposite directions. Then, when they reach all the mirrors, they are going to reach a final detector, and there will be interference. In our case, we are not thinking about interference. And what else do we need to produce that light? We are going to use a strontium-87 sample of atoms. Okay, concretely, the apparatus that we could have, or that we are proposing, is this one. Here is the Earth or the planet in question, which is rotating, for example, in this direction, where we are using the apparatus in one of the poles of the planet. And this is our apparatus. We have here pulse emission, the pulse of 2 pulse emission in the same direction. And they are going to be in this direction, but in that part, they are going to go in opposite directions. So there is a difference in the length paths that they are going to take. That's because of the Sagnac effect that I am going to explain a little bit later. So the theory behind this is that the platform moves, or when the platform moves, there is a difference in the length that both of the light beams are going to make. This difference of the optical path is given by the velocity of the apparatus. In this case, is the velocity of Earth, and the time that the light is flying. These times are given in this form. So this is for the platform. There is a difference in the length because of that movement, and that movement is with this velocity. And for the light, we are going to have the length of the apparatus that they fly, plus, of course, the same. Here we have the same delta L plus minus, and that's and that's what the light is going to do, and that's why this velocity is the velocity of light. Okay, so when we take the difference of those times, t plus minus t minus, there is we have this equation in terms of the length, the velocity of the planet, which is angular velocity of the planet times the radius of our interferometer. That quantity will be called L, capital L, and the velocity then is going to be just the angular velocity of the Earth times the radius, and we just use the expression with the period of the planet. After that, we also consider that the velocity of rotation of the planet and the linear velocity of the interferometer are obviously not as great as the velocity of light. We use an expansion to get to this equation. I don't know why it doesn't appear, but this is we are not taking into account the second order because of that quantity is like 10 to the minus 10 orders less, so it's not so important in our case. Okay, so with those, no, please, thank you. With this parameters, with these quantities, we have this difference of time for the beams that we are measuring. So remember that there is one beam in one direction, the other beam in the opposite direction. So there is going to be a difference in those times because of the rotation of the planet. So one beam goes in the same sense, so it will take more, and the other in the opposite sense, so it will take less. And we get this difference in times that we are going to compute for the Earth. In this case, for example, the exact measured period of the Earth is that number there in seconds, of course. We are taking the radius of our apparatus to be 1 kilometer, and we are going to use the light inside an optical fiber, which give the light this velocity. This is the reference of the fiber optic cable we are using. Okay, so here was the difference. So this is the second order part, which we are not taking into account. So the next thing is that we are emitting pulses from the strontium sample at 10 to the 15 pulses per second. That's quite a lot. And this gives us, please, back into the... So this gives us a precision to measure these small times. So as you can see, we have 1.09, that's almost 1.1, and because of the difference of the order of magnitudes, we have that we are counting when the pulses are received, we are counting 11 pulses of difference between one of the detectors and the other. And that counts 1 second. If we want 1 minute, then we make that accumulative. So, please, okay, so the error and stability of our clock. The exact difference will be this one here. So we are measuring this quantity, we are not measuring this quantity of counts. We have a count on error in the counts. So in that point, after 1 year, we have this quantity of counts, which will be translated to this quantity of seconds, or 8 hours. That means the error in our clock will be after 1 year of 8 hours. We are missing 8 hours. The instability of the clock. We are using a strontium sample, which works like the strontium clocks. So we are going to have the same instability, which is 1 second each 5 billion years. That's something that makes us think that things are good. And for the changing the rotation of the Earth, we have 2.3 milliseconds each century. After almost 50,000 years, we have 1 second of instability. Next, we are going to think about how to fix these errors. So we are counting each year like 31,000 seconds of difference. That means 85 seconds each day. If we turn on the apparatus during that time, then we are going to measure the same day, the same quantity, which corresponds to the time that it had actually happened. And that fixes the error after 1 year. For different planets, we just have this. As you could see in the equation or the formula for finding those delta t, that we just have to know the period of rotation of the planet in question. So for these different planets, these are the periods, and these are the difference in the times that we are measuring, or that we are counting. And according to that, the difference of the pulses received for both detectors will be this line here, in pulses per second. So that was mainly all.
Okay, thank you. Now the opponent, Luis, and is Laura Martinez. So 2 minutes for technical questions.
Okay. So first, do you have the physical dimensions of the interferometer that you are proposing?
Yes, you are.
Can you show it to us?
Yes, I'm proposing a radius of 1 kilometer.
Sorry, what?
I'm proposing a radius here of 1 kilometer.
And this is the same dimension for other planets?
Yes, it could be the same.
You are using an strontium laser to count the the clocks, like the tic-tacs, right?
Right.
And this is the same laser that you use in your interferometer?
No, I do not have an interferometer. So I'm just emitting in one of the sides pulses and on the other also pulses at the same time.
Okay.
Sorry, do you need to know previously the period of the planet to calibrate the clock?
Yes.
And this model of the interferometer don't just only work on the pole?
No, it does not only work on the pole.
Can you please explain briefly the parameters of the delta T, please?
The parameters. So we just have the length, the radius of the interferometer, the period of the planet, and the velocity of light.
Okay, thank you.
Thank you.
Okay, it's time. So we have now 3 minutes for the preparation of the opponent. Who's going to be the opponent then? Laura? Okay, good. So for the public to know and the people in the streaming, so the opponents, they have asked for a timeout. So they have 1 minute more, right?
Okay. Good afternoon, everybody. My name is Laura Martinez, and I am part of the WIS team, the opponent team. So first, I would like to remember the important things that the problems states. So the problems states that we need to propose the most accurate clock that measure time with a temporal resolution of a minute or less using the rotation of Earth. Also, we need to design the clock, and this clock, the idea is calibrate the clock to work even on a different planets. And the final part of the problem is the questions: what certainty will you show the correct time after 1 year? So first, the strengths of the reporter team. First, it's very important because they establish a clear outline that let all the public follow the solution of the problem that they presented. They make emphasis on the problem statement. They clearly explain how the Sagnac-like interferometer works. They explain the setup and the way in this setup work. Also, they clearly state the theory behind this Sagnac-like interferometer. They present the assumptions and the approximation that they did to solve this problem. They estimate numerical estimation of the error, and they include error source due to the change in the Earth period and the emission of the light atom that they use. In this part, I would like to talk a little bit about this on the discussion part, because, do you present the errors in the change according to the change of the Earth rotation, but you didn't talk about this error, but in another planets, for example. We noticed these weaknesses. At the beginning, the rate was very slow, but the thing here is that according to this solution, we need a little more explanation on the final part, that is the technical parts of the equations, of the time shift, and this equation that explained the numerical part of the solution. So this is our weaknesses, because we need a little more explanation at the final part of the presentation. Another weaknesses that we detect is that they didn't care about the coherences in the Sagnac interferometer. This is a very important point, because the delta t that they calculate depends on the size of the interferometer and also depends on the period of the planet. And they say that they changed, the period of the planet changed, but they say that the size of the interferometer is also 1 kilometer. So this delta t changed in each planet. But what about the width of the pulse that they use? If the pulse that they use is different from this delta t, the coherences it maybe didn't occur in the interferometer, so we need to make sure that the fringe pattern will be appear. And there was a little confusion of the orders of the second order, so I would like to maybe in the discussion part to address this part, because it was a little confusing if you use the second order term, of if you didn't use, and why, and what is the meaning of this second order, and what are the implications of avoid this second order in terms of the errors at the end. And there are no clarification of the underlying source. This is a thing that we noticed at the beginning, that is the use of this source of light. but we need to talk about this a little bit. And I would like to propose these discussion points. It's an interesting thing because at the end we notice that in the formula that they use the delta T, they need to know the period of the planet. So it's like a little strange thing because in fact, if you arrive to a planet, how do you, for example, in a spacecraft, if you arrive to a planet, how do you can measure this delta T, well, this time, this period of the planet with the satellite precision or accuracy that they presented, for example, on Earth. So this is like an interesting thing that we need to talk about. We need to discuss about the change in the different literature, in the different latitudes. If the interferometer works similar or what are the changes in different latitudes. That is according to the calibration in another planets. There are some things that we need to talk about this period also and how this period are
now it's time.
Important in the calibration.
Okay, now we have 5 more minutes for the discussion between the reporter and the opponent.
Okay, so we don't have, for example, calculate errors or things, or these detailed things in different planets, because the problem is mainly focused on the Earth. So I took data that we know with a certain precision in the Earth, and I just put them there. To include things from other planets, it will be like the same thing, but it's the same thing. I mean, there is no reason why to think that this is something new. So it's the same. We just have different numbers. For
Okay.
the second order term,
I have a question about this. Well, for example, I think these questions because if you have an error in terms of seconds, when you say that in 1 second there are integer amount of pulses, I don't know if this, you say also that are errors in the estimation of the seconds, but when you talk about the times in another planets, you talk about hours, and I think that is more precise if you talk about these hours in terms of seconds or in terms of pulse per second, I think. The precision of the time of the period in each planet are very different. So I think it's a best idea to talk about the pulse per second or all these times and seconds in order to put into a same precision and accuracy. I don't know if you are in agreement with me.
we are just taking times from different sources. Well, I put the times like this because it's easier to think about these terms like days and hours for the rotation of a planet and not for about seconds. Because if I put the number of seconds are large numbers and maybe they are not so understandable. So I just put them here, and here I have the second part, and that's how I really calculate this.
Okay.
I would like to emphasize that this is not an interferometer. I'm not using an interferometer. So there is no need to have a great or big current length in the fiber optic cable, but there is anyway optic cable which have length of 100 kilometers. So this will not be a problem because we're just having one like 10 kilometers of the length of the total path.
Okay, let's talk about the calibration in different planets. I think that maybe a source of error is to use the same size of the interferometer. What do you think about this?
Well, the parameters that determine the difference in the times are just that length and the period of the planet. So the period of the planet is what is different in each planet, and that's how the calibration should work, because as I said, is the difference thing in each planet. So we could change this and obtain different delta times, but I don't see like the need to do this, because if I change, well, I can measure better or more precise or not so precise times, but it depends on the scale, but also on the period of the planet, and we could fix just one parameter.
Okay, I have an improvement or a suggestion for you. I think that the way to use this formula is needed to know the exactly period of the planet with a high precision. So I suggest to use also the Sagnac interferometer in order to obtain the angular velocity of the planet in order to calculate with high precision the period of the planet, because I think that this is a sort of error that we need to take into account until here.
Okay, thank you. Yes, you asked me about the light source.
Yes.
So please, more. Another. The details of the light we are emitting. So we have a strontium atom sample. And basically, this works like this. We hit the atoms with blue light in order to make them cold, and then they made cold because the atoms are going to emit the photons. So next, one before. So we are having please one before. We are having here.
But no, we have time. Okay. So we have right now. We have 2 minutes for clarifying questions from the reviewer to the reporter.
Yeah, I know. I think that I can start with the opponent. And what are the other source of error that you think that do be included in the model?
I think that one source of error is the use of the calculation of the period of each planet. I think that is one source error. I think that, okay. Another thing, maybe they didn't talk about the latitudes. I think that is an important thing to take into account. They didn't talk if they use the Sagnac interferometer or this experimental setup in the North Pole or in which place of the planet.
Thank you. For the reporter, some of the numbers that you're showing have up to 8 significant figures. Are you sure you can know these numbers with that kind of precision?
Please, the number.
Just yes or no?
Yes.
Okay, for the opponent, you talk about the measurable phase shifts. You know the range in what the phase shift is measurable?
Well, it depends on the detector, but I know that, yes.
Okay, thank you. For the reporter, the opponent mentioned the coherence of the light. Do you believe this is important? And do you believe this might have to do with the dispersion in the fiber optics?
It is not important. It is important for a laser, not for our apparatus.
Thank you.
Question for the reporter. Is a question in the I think that the slide of the setup, in what you have the circles. I want that you can explain me what are the black circle and the green circle in Sora answer, please.
This is the apparatus, and this is their light sources. This is one, and this is the other one.
Okay, thank you. For the reporter, you mentioned you can do this in Uranus and Neptune. These are gas giants. Are you sure you can do this in planets with no surface?
This one cannot be done, but there is something that can be done instead.
Okay, thank you. Now we have, for the preparation of the reporter presentation, 1 minute. Of the opponents, of the viewers. Okay, it's time. Time starts right now.
Thanks. Okay, hi to everyone. My name is William. I'm going to be your reviewer today. So I first want to recall the main objective of the problem, and is propose the most accurate clock. And this part, like the team of the university Unal said is proposed. So with that in mind, let's continue with the next. So I'm going to first give us the strengths of the reporter and the strengths of the opponent. So first, I love how you make that presentation because it's a good one and it's very clear. I mean, it's easy to follow and the ideas are very nice. It's clearly a teamwork between all the members. And there's something that it's very interesting is the optical method, right? Because when this is a very hard problem, and when you solve this, there are many, the first ideas are like mechanical methods, but that something came here with an optical method, it's very, very nice. So the next thing that I want to make a great point is that they show explicit numbers, and that is amazing. Of course, they work on all the objectives of the problem, so very, very nice. On the opponent, I have to say, I really love the attitude during the discussion. They called attention of their sources and try to clarify misunderstood points, and that is very useful, at least for the reviewer team, because we have some lags in some points in the presentation. Okay, another stuff that is very important is that they remark the comment of the attitude, that is that duality between the mechanical part and the optical part of these kind of setups. And they show a clear intention how to improve the viability of the setup of the team in other planets. So, what I want to discuss now, first of all, I want to have a time between all to clarify the setup. Interferometer or not? That is, we need to clarify this for the preceding discussion. A very interesting thing that the use team say is that they can use the sine effect to measure the rotation of the planet that they are. So I want to get a little bit deeper in that and look at it. Okay, so the procedure is set in anywhere, like my team member said, and so I'm going to put some discussion rules. If you want to talk, please ask the hand. I give you the mic, and when the team members
now
want
it's
to
time.
talk.
Thank you very much.
Okay.
Now is a discussion between all of you.
Okay, let's come here. Okay, so let's begin with the first. Yes, it doesn't matter. So we want to talk interferometer or not.
No, it's not an interferometer. It's just a device with two light sources and two detectors. I would like to remark that I said that the coherence length was not important because of this, because this is not an interferometer.
It's not. Do you agree with that? Because it's very strange that you say that it's not an interferometer, but in the outline of your presentation, it seems like an interferometer.
I think that interferometer, yes, but in that way, no. I think that the power of the interferometer can be used in a better way, in order to measure the precision time of the rotation of air, and maybe use the source of light that you use to have a pulse in which can you characterize the time and the time of the clock in terms of this width of the pulse and with a
Okay.
value of the.
Okay, that was very, very interesting part of they say that you can use the interferometer to measure the Earth's period. Do you think that will improve your model, or what add something to it?
Yes, actually, I think it could. We could just do the opposite thing, and then we have the period of the planet.
Okay, so there's other thing I want to talk. You asked about it. Is the viability on other planets? That is a main topic of the problem, and I think we must make clear of them here. So in the question, they say that in some gaseous planet that will be different. So I need that we clarify this.
Can you please repeat the last part?
Okay, so in the questions, my partner say that in other planets, like gaseous planets, this setup will be complex. So how you could help the UNAL team to solve that?
Well, one problem is the size, because the delta T depends on the size and depends on the period. So one important thing is, if you increase the size, you need to make sure that the power of the light source is enough to do this trajectory. So you need to recycle the power, for example.
So what do you think about that?
Well, I was focusing on the fact, that in a gas planet we can't have this setup, so we can't have, but we have like another setup using also general relativity corrections like gravitomagnetic effect and clock effect that is shown in the slide.
Ah, do you do that?
Yes.
Oh, right. That's cool. That's very cool.
Works also in planet.
Okay, the last part, we have a minute, right? So it's talk a little bit that duality. How do you say that you like simple solutions, but you are showing a very interesting problem in a very non-conventional way. So what are the advantages of this kind of problem?
Precision and stability.
What do you think about that?
Yes, precision, but in the period time, and also the setup. The complete setup is very important, for example, in terms of planets that are a low rotation period, and also the latitude is another important thing to build this setup.
Okay, other thing that...
Yes, latitude is important because of the time will also depend on the latitude if we consider a different latitude. But we are putting them in the poles of the planet because it is easier and we have greater delays or difference of times.
I have a suggestion. I think that this experimental setup works in another latitudes, but the thing that we need to do is only align this interferometer in order to have the same rotation as the north one.
Okay, thank you. So now we are going to have the general discussion between the teams. That means that any member of any team can participate.
Okay, first of all, let's remember that this discussion is first going to help the problem of the UNAL team to make it better, right? So only things that make better the problem.
Right, thank you. It's really a question for both of you. The reporter made it clear that this could be improved with relativistic effects, but they don't show any metric. Do any of you have ideas on how we could develop such a metric to include relativistic effects?
Okay, so I first begin with
the problem with the relativistic part, for example, I have this calculation and the times we get with those corrections that are very small to consider. So I don't have the whole development, but there is like the result.
Okay. What do you think about that? It could be improved with that way?
Yes, but I think that are another improvement that are more important than this in terms of importance in numbers, I think.
Okay, someone else have to work?
To the reporter, please, what do you think as the most important error source in your setup?
Remember that this discussion is to help the reporter, not for
us. If we know what is the main error source, we can improve the experimental setup.
For me, the biggest error is the fact that the clock, as I shown at first, there is an error after 1 year of 8 hours. So that's the biggest error, and that's the one we fixed.
Okay, so I ask you to the opponent, how do you improve? Asking again the question of your team member.
Okay, first I will use the Sagnac interferometer to measure the period of each planet. And also I think that we can use the pulse of the light source that is a constant time that it didn't depend on the planet to fit this pulse on the rotation on the time of the rotation of each planet in order to have this time in terms of pulses and to have the precision in terms of the width of the pulse.
Okay,
of each pulse.
That's very nice, man.
Keeping in line with what you just said and with what your teammates said regarding precision and the errors, some of the numbers they showed had almost up to 8 significant figures. Do you agree with this? Do you think this is a plausible thing that we can measure with 8 significant figures of precision?
Sorry, I didn't understand you.
Some of the figures they have, they say they have precision up to 8 decimal points. So do you agree that we can measure this with that kind of precision?
With the data that they present, I'm not completely sure because I think I have doubts about the precision of the period of time that they use to calculate.
I want that the report to clarify.
Okay, so we can't actually measure all these numbers, but when we propagate those numbers, we have errors after some significant numbers. So that's why I put all those numbers.
Thank you.
Okay.
Another question for the reporter. do you consider using other type of elements of the short life? You use here, I don't remember the atom, but for example, cesium atoms or something like that?
Strontium atoms are actually more precise than strontium atoms are more precise than cesium atoms, and we could also use a lattice of tungsten light, which is heated by extreme ultraviolet, that give us attosecond precision. So in principle, it could be done.
Okay, thank you.
Okay, that.
For the opponent, your teammate just mentioned that might look for other sources, not just strontium atoms. Why do you think this is important, and what do you propose we use?
Well, we're talking at different kind of sources in order to make sure that, for example, we have an integer number of jumps of the inside the atom. That is exactly number of seconds or whatever. Is to make sure that there are, for example, 10 pulses or whatever. This is the general idea.
Okay.
Thank you.
How do you control that? That if you say that, how do you control that?
These pulses? No, well, the way to control this is to choose the atom, for example, this kind of atom, to make sure that this time is exactly number of times. This pulse at exactly 1 second, 11 seconds, or whatever. This is.
Do you have something to add about that?
Yes, we can control the clock or the precision is in the same way that it is do it in the atom clocks.
Okay, an intervention.
Oh, here we talk about that because we can use what Laura says, a laser in the Sagnac interferometer that you have, and you can use that to measure the period of the planet precisely. That was we are talking about the light source.
Okay.
Thank you very much. Now we have 1 minute for the reporter for the final remarks. Nicolas?
So possible improvements. Well, the thing of the latitude, we talked about it because there is a complication with the latitude. It's, for example, in the equator. So there we have delta t like infinity. But we could do some modification if the clock is not in the pole, in order to work as in the pole, as the opponent told us. Something else is to consider for example, gas planets, because they don't have a definite surface, and we kind of consider that, but we have to improve in that. Something else is the fact that the period is have to be known. So we could have an interferometer to determine that period before we use the clock.
Well, thank you very much, Nicolas. We have now 6 minutes for the questions from the jury.
Correct me if I'm wrong, but as far as I remember, the position of the rotation axis of the Earth is not exactly stable. It moves from year to year, seemingly chaotically, and we speak about the distances around 10 or even tens of meters each year on the surface of the Earth. Did you account for this phenomenon when estimating the precision of your device?
I took the amount of time that, or the difference in the Earth's rotation after a long time.
It's not an Earth's rotation, it's the position of the axis. As far as I understand, you want to build your device around the pole. Yeah?
Yes.
But the position of the pole is changing from year to year, as far as I remember. I cannot check now, but as far as I remember.
Yes, you mean the physical position?
Physical position of the Earth on the surface. On the surface, it moves.
Oh, okay. Okay, so the surface with respect to the rotation axis.
Exactly.
That could be a problem in principle. Yep. So we didn't take that into account.
Okay. Second question: how exactly do you want to plan to count the pulses? Other in the market some electronics which can deal with such frequencies and collect the number of pulses?
Yes, it will be done in the same way that is done for atomic clocks. We are just changing the detector from one position to the final path of the beams, and I think that is made with photoelectric effect.
Okay, thank you.
Okay. Hi. Can you please explain again the experimental setup? And you were talking about optical fibers. Where are the optical fibers? The setup where I didn't get a picture of that.
Yes, this is the first one. I didn't explain that, but in principle, the optical fibers are.
But you are showing me there the Sagnac interferometer, and now you were okay. Now this one.
Yes. So, here they are the beams, but they are inside of fiber optic cables.
No, which beams? I don't. Here, when you place this slide, it says pulse emission, pulse reception. What is that? Which pulse?
Well, we don't have beams in the sense that like a continuous beam or a laser. We have pulse emission inside the fiber optic cable.
So no, but the red rectangle, what is that?
That's the physical place where we are emitting the pulses and receiving them. It's like a base or something like that.
So where you have your strontium atoms?
Yes.
So okay, but now I'm taking too long. Okay, so you have your strontium atoms. You shine them with a blue laser, you said.
Yes.
So then what happened?
When I hit them with a blue laser, I have an image. I hit them with a blue laser, they get excited and then emit photons, they get cold. We trap them with red light in a cubical lattice, a very separate one of each other, so we can have the same situation for each one without interact that atom with the other. And then I again hit them with blue light with the resonance frequency of the atom, and then all the atoms, thousands of strontium atoms, emit the light which we are going to direct for the next one. The light that we are going to direct to the fiber optic cable.
But can you go back? Can I continue? Or someone has another question?
Okay.
So then we can discuss the setup.
Okay.
You talk about errors considering Earth rotation. So, but I guess what the question that Vladimir asked before, you didn't take into account the exact location of the North Pole. I mean, the errors in the Earth rotation you're considering what precisely?
The error in the rotation of the Earth after several years, or?
But as a result of what?
As a result of the fact that the Earth is losing its rotational velocity.
Okay.
So, okay, 50 seconds. Yeah. So go back, please, to the setup.
To the second.
To the setup.
To the setup.
40, 42, 41. There. So now we know what is the red rectangle. So then, but this strontium is emitting pulses of light, or what is it emitting? Light
Yes.
pulses?
Yes, we have a lattice of
Okay. So
atoms.
what? So you say you emit a light pulse. So what happened?
The light pulses make this direction inside the fiber optic cable. They turn in this direction. The other one turn in the opposite direction, and again they get
Recombine
detected.
in the atoms. And what happened there?
Where? Sorry.
They recombine in the atoms, but now the time is up.
Yeah, time's up now. So we have, now is 1 minute for you to decide your marks, your grades. Well, thank you now. So I'm going to ask you to raise the numbers, the grades for, first I'm going to start in a different order. So for the opponent, yeah? Opponent. Good, that is 877-589-8799. Good, thank you. Now, for the reviewer. Reviewer, yep. 886-478-9767. Thank you very much, Judith. And now, for the reporter. Reporter, the grades, please. 886-548-7765. Great. We have almost completed the second round, except for the maybe the comments from the jury members. Does anyone want to make a comment, suggestion, etc.? No question.
No, comment.
Comment.
The setup. Like each time that someone was asking something, it was becoming more complicated. Cold atoms, blah, 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 blah. So my comment is just, I think it could have been explained better, that experimental setup. And there was also a big confusion if there was the interferometer or not. So just that.
Okay, good. Well, thank you very much. So this is the end of the second round of this physics final. We have some pastry there, so you are very welcome to eat some pastry and then to come here. So about 10 minutes. Excuse me? Well, it's for the basically for the jury members and the participants, and then if we have some extra, it's for the attendants there. second round. The third round. So we asked the members of the jury to come here. And the participants, please. Pues allá está.
I need a space.
Some space here. we have 1 more minute to go. Okay, you're going to start right now.
Okay, good afternoon, everybody. My name is Juan Manuel. I'm part of the UIS team, and I'm going to be the reporter of the problem number 14, called Jumping Beans. Okay, first we want to clarify on the problem statement and the 2 questions that are involved here. The problem says that a simple toy called a jumping bean can be construed by putting a metal ball inside of a pill capsule, like you see in this figure. And when you put that system over an inclinated plane, you will obtain this movement over here. So the problem asks for 2 different things. The first one is investigate its motion, and the second one is find the dimension of the slowest and the fastest jumping bean. So we made a theoretical approach, a simulation approach, and finally an experimental approach in order to prove if our theory and our data fits very well. First, I'm going to explain the theoretical approach. We decide to analyze this motion in 2 different parts. The first motion is the complete motion, but when you divide them, you have the movement of the sphere inside the pill, and the second movement is the rolling of the entire system, okay? So the parameters important in our theory are the masses of the sphere, the pill, the total mass of the system, the properties of the capsule that are the length and the cylindrical height, the sphere radius that must be almost the same of the sphere of the pill radius, and finally the inclination angle that is very important here. The conditions that we use to produce the theory are the capsule radius and the sphere not be exactly the same, but needs to be very similar. All the movement will be described by one plane, but we will abort that point later. And finally, we need to include the rolling condition on the capsule inside the pill and when the pill is rolling up too. So the first point was trying to not knowing what's happening when the sphere is rolling in the pill. So we have Newtonian mechanics. And something very important here is our system of reference will be the same always. We have the y-axis, the x-axis, and z comes from the slide. So describing Newtonian mechanics inside of this and using the rolling condition, we will have the final time in which the sphere will hit the pill over here. After that, we can estimate the final velocity that will have the sphere in that moment. And the most important thing of here is in order to analyze what happened when the pill is rolling again, we need to estimate the angular momentum with respect to this point, because we will use the angular momentum conservation to describe this problem. So we have the angular momentum before the hit and after the hit. And with that, we will notice will be the angular velocity on the entire system at the beginning. And it depends on the inertia momentum, the total inertia momentum of the system. The total momentum inertia of the system is very complicated with respect to this point, so we decide to make the calculus separately. The pill has a cylinder part and 2 sphere shells. And using parallel axis theorem and perpendicular axis theorem, we can build this expression and add the inertia moment of the sphere with respect to this point, and we have this expression over here. Replacing this expression on the angular velocity that we obtain, we have that this long formula is the initial angular momentum that will describe this movement. But we know that after that hitting, we cannot use angular momentum conservation anymore because the gravity will induce a torque. So we need to use angular dynamics. And we know that each one of these points of contact during the movement is different. So we have variation on the inertia total momentum and variation on the arms where the torque will be done. At the end, we have this entire second order equation that is very complicated and it's non-linear, so we need to have numerical solution of this in order to estimate what happened during this movement. So, in summary, we have initial conditions of the sphere. That initial conditions using analytic solution of Newton equation plus angular momentum conservation will give us the final conditions. That final condition would estimate the initial angular velocity that will be described by this movement. Using that conditions, we use numerical solution of the angular dynamic to have the final conditions over this movement, and that final condition will be again the initial condition of this movement, and at the end we repeat this process till the capsule reaches the final part of the floor. Now, this is our theory predictions. We only vary the length of the pill and the mass of the pill, keeping constant all the other parameters. And what we can see here is at the end of the movement, this is the x distance and this is the final time. At the end of the movement, the shortest one was the fastest one, and the longest one was the slower one, okay? That's very important here. Now we decide to go even further and try to make the simulation approach of this problem, trying to understand what happens if the dimensions of the pill are very different from the sphere. We use abacus in order to simulate this, and we use exactly the same materials that we can obtain in the experimental setup. So what we obtained was this. The sphere began from rest and start rolling, make the movement of the pill, and that process will repeat and repeat again. But what's very interesting is that when you see what's happened in the upside down view, you will notice that the variation on the dimension of the pill of the sphere will lead us to a chaotic or random movement on the angle respect to the initial position. So we don't have like one description in one plane, the movement, you have different planes, but at the end you can include this delay on time in the equation that we presented before. Now, our experimental approach. We use 6 different types of pills from this length to this length. We use 3 different types of surface, increasing the friction in that direction, the inclined plane, and we change for 3 different angles. Each experiment was carried out 5 times. And we record that. The data collection was made by video processing using tracker. And what we obtained is here. This is the upside down view, and this is the x distance, again, the final time. And we have all the capsules over here. What you can see here is that the smaller one is the fastest one, and the longest one is the slower one, exactly what our theory predicts. And this is the movement that can be explained by the difference between the dimension of the pill of the sphere. Now we only be talking about the 3 first capsules in order to have better conditions to see the graphs. And what we can see here is when you increase the friction in the first 3 capsules and you take into account the error bars, the surface in which the capsules reach the floor first are the surface number 3. So we'll be interested on that. Now, when we keep fixed the surface and when we variate the angles, what we obtain is if you increase the angle, you will decrease the final time in which the pill will reach the floor. So we were very interested in analyzing the biggest angle that we could estimate in our experimental setup, that was 20 degrees. Now, when you keep constant the surface and the angle, and you vary the capsule length, we obtain what we previously see. The shortest one is the fastest one, and the longest one is the slower one. And this is the movement that you can see only for the first 3 capsules, and this is the upside down mode, okay? Now, we need to compare the data with our theory. The first comparison is changing the capsule length and comparing the final time. So, the red points are our experimental data, and the black points are the theoretical data predicted. Okay, so we can see here that the theory and the experimental data behaves exactly the same. And when you see the errors are around 0. So we have the certainty that our theory includes all the relevant parameters necessary to describe this movement. Now, what happens when the angles? We have also the same behavior, and the errors are again around 0 points. So we obtain that the theory reproduces exactly what we can see also in the experiments and in the simulation part. Now, what happens if we compare the x distance against the final time? We obtain this over here. This is the predicted one, and this is the experimental data. So you can see that this theory fits perfectly with almost all the points of the experimental data, and that's because the theory has the perfect parameters or the most important parameters that describe the movement. So finally, and to conclude, I want to see that the motion of the jumping beans can be explained by using the Newtonian mechanics, the angular momentum conservation, and finally the angular dynamics, where this formula is the most important one, and that will explain the motion completely. The dimensions, that is the second question, the dimension of the fastest and slowest beam for a given inclination will be determined by analyzing the maximum and minimums of our theory. And finally, we have the dimension, the real dimension of our beams. That's the fastest beam has 87 centimeters of length and a mass of this over here. We keep constant the radius of the sphere and the mass of the sphere. And finally, the slowest beam in our solution was the longest one. This is the value for the length, and this is the value for the mass. So, thank you very much.
Well, thank you very much. Now the questions from the opponent, technical questions.
I want to quote you on something you just said, that your model had and I quote, a perfect parameter. Are you implying that there's nothing we can improve of your model?
No, that doesn't imply that. We can improve the model. So.
Okay, I have another question, and is what is the method that you are using to feed the data?
The method to feed the data?
Yeah.
We follow this, the circle that I explained in the summary. We follow that using the initial parameters of our pills and our spheres, and we can plot this graph. And we compare with the experimental data. We don't fit the theory. We make the graph of the theory using the parameters of the data.
Okay.
Do you consider the thickness of the pill in the moment of inertia?
No, the thickness wasn't considered there.
Okay.
At the beginning of your presentation, you mentioned conservation of momentum. Are you implying that in this system, angular momentum is conserved?
No, I say that it's conserved only in the first part. After the pill starts
Thank
rolling,
you.
it's not conserved anymore.
Is there any dynamic friction coefficient in your model?
No, in the theoretical, the only important thing of the friction included there is the rolling condition.
Thank you.
No, the coefficient.
Okay, in this slide, what is the origin of this black line, the theoretical line, the equation?
The equation is the equation combined with the two methods, the Newtonian solution for the first part, and then the numerical solution for the rolling part, and then again.
You showed a 3D simulation of what's going on, but you make no mention of the model behind that. You just seem to use an already built-in application. Do you understand the model of that 3D simulation?
Yes, it's a finite elements simulation using Abacus.
You say you need a solution for a nonlinear equation. At which point do you show the solution of that?
No, we use numerical solution because we doesn't have the analytic solution.
Thank you. Okay. Well, good. Now we have 3 minutes, and that will be for the preparation of the opponent. That will be Juan David? Yes? Okay, good. Okay, the opponent is ready now. We set the time for 5 minutes for the opponent's speech from now.
Okay, my name is Juan David Nieto, and I'm going to be the opponent. Now, so let's check out the problem briefly. We have that the problem states that we have a jumping bean that's placed on an inclined surface, and it's going to tumble down. I think we understood well the motion with the presentation from the WIS. And I'm going to make emphasis on the two main important points that were investigate the motion and find the dimensions of the fastest and the slowest beans for a given inclination. Okay, so let's check on the pros and cons of what we consider. Now, we considered they had a coherent presentation on how they attacked the model, at least experimentally. They had a very strong experimental approach. They took in account a very large amount of data, including friction and including various lengths of the beans and various masses for the capsules and the balls. They showed a pretty good simulation that, although it wasn't very precise with the model they were presenting because the ball was significantly smaller than the length of the capsule, but either way, it showed the dynamics. And they considered a very large amount of variables in their experimental data. Now, let's talk about the cons. In the first slides, they said that the angular momentum was conserved, and it's not conserved in any of the two movements since the torque in neither of the two movements is 0. This is a pretty serious error, in our opinion, theoretical error. Another thing is the relation between it wasn't really clear if they found a relation between the ball and the capsule to obtain a jumping bean. I think maybe you guys took a very large amount of experimental data. I'm pretty sure you encountered beans that didn't present the phenomenon of jumping beans. There was the relation between the parameters of the dimensions that optimize the falling time. What I want to say is that the problem specified that for a given angle, you should find the dimensions of the fastest jumping bean. You took the highest angle you could find, and in our opinion, that wasn't the statement of a problem. It was, if I give you an angle, you should be able to tell me what are the dimensions of the fastest bean that is going to optimize the falling time, and you gave us one bean for a specific angle. So the other one was the loss of energy due to friction forces. You tested experimentally a lot of various friction surfaces, and that wasn't considered experimentally. And there weren't a lot of conclusions on the relations of all the parameters you guys considered experimentally. Again, you took a very large amount of data, and there wasn't a clear conclusion about given a certain surface with friction and a certain angle, what parameters of the dimensions of the beam optimize the falling time. And, well, the theoretical model that you guys proposed was very different from all the experiments that you guys considered. Okay, so I want to make a remark on the first point. I think it's very important that it is understood why the angular momentum isn't conserved in neither of both of the processes of the movement of the jumping bean. And I think that this is going to be the main theoretical difficulty to be approached on in this problem.
Okay, we are ready. Now we call the reporter to the stage for the discussion.
Okay.
Good. You can start now.
Perfect. I want to clarify that of the angular momentum, please. What we put in the theory was that here, around this point, when the sphere hit the capsule and just before the capsule starts to move, the angular momentum will be conserved. But during the movement of the entire system, that doesn't happen. It's only happened in this moment.
Are you saying that the sum of the torques on the ball when it is at rest in an inclined plane is 0?
No, I'm saying that for this point, the sum of the torque is 0.
The ball will not rotate if the sum of the torques around that point is 0.
Yes.
And it rotates.
But it rotates because the sphere transfers angular momentum to the pill, and the pill will start rotating.
I'm not sure if you're clear with what I am asking you.
What?
The ball cannot rotate if angular momentum is conserved. The ball is at rest.
But here, in this point, the ball is at rest. He reached that point
And it
hit the
starts
capsule.
rotating, yes, and it starts rotating.
And it starts rotating the entire movement, the pill plus the sphere that is there. Where is the problem?
I am sorry. There is no possible way that the sum of the torques on the ball is going to be 0. We can check. We can change the topic if you want. Let's change to to another. Okay. I want to discuss the friction. You didn't consider friction in your model. Why do you fit experimental data with a model that you vary friction? Yes, you vary the friction in your model. Why do you fit a model that isn't considering friction with varying different friction surfaces?
What happened here is that we use the non-rolling condition. So we need to guarantee that the friction of the surface will be able to follow that condition. So if we increase the friction of the surface, we can obtain that at the end there was no rolling here. If the friction decrease on here and here, we have that the pill and the sphere can roll inside, and that doesn't fit our theoretical approach of that having the friction necessary to non-roll.
Okay, so you're telling me that you found the minimum amount of friction between the surface and the pill that allows the jumping being phenomenon.
I found experimentally the surface that behaves like that more behaves like that, okay? And when we, in the simulation, when we can see what happened with the friction and what are you saying, for example, where the friction is low, you can put it that and there's no roll. That was happened. And when the friction is increased a little bit, the movement doesn't happen because the capsule is sliding. It's not following the rolling condition. So we need to guarantee that the friction of the surface must be the necessary to follow that condition.
Okay, this is just a little comment. Why did you only show points in your data and you didn't really fit any curves on the points?
In which one of the
all of
graphs?
you don't fit any curves in those data points right there. Why didn't you fit that to
here? Because we are only presenting their experimental results, but after here we have the fit with the theory, and if we go further, we can compare it with the fit of the three first capsules, for example.
Okay, can I go to right here? This is the x distance. Why don't you show the distance? Okay, this is the x distance, if I am correct, is the distance the pill is moving in this direction,
right?
right?
The movement along the plan.
If the time that is being optimized is the falling time, why don't you show the time of z in terms of the graph of z in terms of t?
Wait a minute. Here we have the reference system that we use. Look at that. X is this axis.
Yes.
You need to minimize.
Okay. Okay. Okay, I think time's up.
Guys, almost. Okay. It is almost, but I think, yeah? Quick question, 2 seconds? No, it's okay. So the reviewer, now we have time for the reviewer clarifying questions.
I don't understand. You consider the ball fits the cylinder, right?
Yes, it stick with the cylinder.
But I see that it doesn't do that in the video where you show it.
In the simulation.
Yeah, why does that happen?
Because the condition for the theoretical model is that the radius must be almost the same. But if you, in the simulation, we change a lot that radio, and that doesn't happen.
I have a question about the simulations. There, how do you define the constant of interaction between the ball and the cylinder?
The constant what?
The constant of interaction between the ball and the cylinder.
We use the mechanical framework of abacus, and that is included there, and we solve that with finite elements.
So you use the default constant interaction
yes,
that you use
we include the dimensions of the pill, the dimension of the sphere, the material on the pill, on the sphere, and that's all.
How many did you make the experiments? What is your statistics?
For each one of these points, wait a minute. For each one of these points, there are around 5 experiments. Each one of these points. Sorry, no. For each one of these lines, the entire movement, 5 experiments.
So, for example, do you have for the it is like how many cycles did you measure?
Well, it's not how many cycles, because tracker it's difficult to measure how many cycles it's making.
Okay, for the can you pass to the last slide, please? No, the last one. Okay, for this one, it is for a tracker for the ball or for the center of geometrical center of the cylinder?
For the final part of the pill.
Okay, thank you. 1 minute for preparation of your presentation. Reviewer ready? 3 seconds. Time is going now. Time out. Okay, 1 minute time out. What we are going to do next is 3 minutes they have for their speech. So the reviewer speech, 3 minutes.
Yep.
But now it's 1 minute time out, right? Okay. During the speech. It's because they took too long, right?
Okay, go back to the beginning.
So to explain this, we were already something like 5 seconds. Now they are ready. Good.
Okay, so the main problem is to investigate the motion of such toys and to find the dimensions of the slowest and fastest beans. So in the reporter's speech, I saw good diagrams and clear figures that help us understand the main problem. He had a clear speech. I like that they had a simulation approach, which in the tournament I didn't saw much of that. They had experimental results, which are very important. At the end, they showed a good fit of the experimental data with the theory they developed. And he answered at the end the question of the problem, even though they did it partially for just one angle. In the opponent's speech, I think he did well considering the pros and the cons of the reporter. He acknowledged basic concepts that lacked in the solution of the problem, such as the conservation of momentum. Also, the characteristics that make necessary the setup, the experimental setup, such as the friction of the plane. And also the importance of the angle, because how do you choose a default angle? You should have a parameter to know which angle to use. They did use different angles in the experiments, but at least we didn't see how that connected to the theory they did. And yeah, they also spoke about how the theoretical model differs from the experiments that they carried out. So the discussion was good because they spoke in almost equal times. The opponent's team showed good teamwork, as well as the reporters. They should have better communication to agree in the things they say and to focus on the things the opponent gives to improve the problem. And now I think we should focus the debate on these topics.
Okay, good. Now we have some time for discussion between all of you. Okay.
So first, I like to talk about the friction importance in your model, and if you think it is really important, as the opponent said, and why do you think it's important?
Okay, the friction in our model is included in the non-rolling condition. That's the only point that includes the friction, and we think that is very important, like the simulation shows and experiment shows.
Okay, ideally when you try to make a theoretical approach on how to, with the condition that the friction is only going to affect your system so it doesn't rotate, you can do that. But experimentally, it is very difficult unless you actually do a series of trials until which you can actually assure that the friction between the surface and the jumping beam is exactly the necessary to only cause rotational movement. Yes? So I think it is relevant, depending on the total energy of your system, that you consider friction forces, because if the jumping beam is small and you use a certain surface with a large amount of friction, you need to consider this because your system is going to lose energy.
Okay, so now that you both agree that friction is important and that you actually took it into account into your model, I wonder if you get some cases that contrast with the theory, like in experiments with different surfaces. You could get that it can't tumble, so the ball goes down, but it doesn't have enough friction to make it tumble, so it slides.
To make the second movement, yes, we saw that we use another capsule that was the most longer one, and that happens there. That's the limitation there.
Do you agree that they obtained those results in their model?
I am not completely sure if they obtained it, since they didn't show it in their data. They didn't show a limiting case in which the beam, which the ball touches reaches the final part of the capsule and slides or doesn't rotate.
Yes.
What happened if we include that is that toy, that system doesn't follow the behavior of the jumping beam. That was the principal idea of the investigation of the motion of the problem. That was the problem.
And since you also considered the friction of the plane, did you thought about considering the friction of the cylinder and the ball? Because how do you assume that if it rotates, it always does it, or if it slides?
Yes, that's something very important to consider. If, for example, you don't have the necessary friction to the heat of the sphere match perfectly with the pill, you will have the sphere rolling there. But in our case, we decided that that was extremely complicated to model, and we decided only to use, again, the rolling condition, the friction necessary to make the sphere roll.
And for you, how do you think that they could implement or add that friction into their model, if there is anything else that we can take that is more important than that?
They could definitely include the friction forces if they consider maybe Lagrangian or Hamiltonian mechanics. There are ways they can include those friction forces in their calculations, at least theoretically.
So now we have the general discussion, meaning that any member of the team can intervene.
Okay, so you can speak.
I want to talk about the simulation, the comparison between the simulation results and the analytical results and the experimental results, because we can see in your simulation that the capsule is really sleeping. So how can you compare these results, and who can you implement in your theoretical model?
Which one of the simulation, with low friction, medium friction, or high friction?
I think that in all of these simulations, the capsule sleep.
In all of them?
Yeah.
Can you put it the simulation of the maximum friction? How can we include that theoretically? That's what we're explaining. Well, that's very difficult to include, because if we don't have the rolling condition, it's very complicated to model that. No, this is mid friction, the maximum friction. But in the maximum friction, where you have the rolling condition, you can see that that doesn't happen. Sorry. The capsule doesn't slip there when you follow that condition.
Okay, I think we talked about friction and most of the discussion, so we can pass on to how to improve the model that you already have. So we should see the limiting cases of your solution. So which are those limiting cases, the ones you saw you have and the ones you think he's missing?
How can I improve my theoretical model? When the capsule is almost equals to the sphere? And
yes, the limiting cases are when your theory doesn't longer work because it's
the
too
limitation.
extreme. Okay.
Yes. We have one important limiting case, is that is when the when the transfer of angular momentum occurs, if the angular momentum that is going to be transferred to the pill is not enough compared with the pill length. For example, if you have a giant pill that doesn't rotate, and that's where our model, for example, breaks there. That's the limiting case. And to include that, that will be very difficult, but we can think about how to improve that.
I think you guys with the data, you took a very large amount of experimental data. I think that maybe varying the length of the pill, you can find the limiting case, at least experimentally, which is what you guys actually are, that's your strong part. I think experimentally you can find that.
Okay, perfect.
Okay, let's give.
Okay, for the opponent team, well, in our theory, we assume, or well, we studied a special case when the radius of the sphere is almost the radius of the spherical part of the pill. How do you, an idea in order to improve their model, how do you can model the cases in which the radius is lesser than the radius of the pills? Because as in the simulation we can see there are bounds inside the pills. So how can you improve this model taking into account this behavior?
Absolutely. This is kind of relating to one of our technical questions regarding your simulation. I asked you if we had a really good understanding of that 3D simulation, because that's where that phenomena you're talking about comes up in the 3D simulation. And I think that to improve your model, because you have done some great things, but to improve it, we should really focus on trying to understand the physics behind your 3D simulation, not just plugging in some numbers on some already built-in app.
Okay, thank you. I think we should change topic. We only have 1 minute. So in the angles you show, you have 20. What do you think will happen if you change that?
If we increase that, the capsule will arrive to the floor faster.
For other angles, how do you think the behavior of these plots will be?
Will be almost the same, because it's a parameter that can we include in the equations.
Okay.
Can you show me your conclusions, please? Okay, so what do you think that the characteristics of the beans that you showed right there are also going to be the fastest and slowing beans if we vary the angle?
No, these are only for the experimental results that we obtain.
Okay, I think the time.
Okay, I have a little suggestion, and is that a Lagrangian analysis, it is impossible because we have friction, and it needs conservation of friction.
Time's out now. Thank you. Now we have 1 minute for the concluding remarks by the reporter. Please, Juan Manuel.
Okay. First, thanks all of you for the fruitful discussion. I think that's something very important in physics and in science in general. You need to have persons that doesn't agree with you in order to improve your solution, and that's the idea of this tournament. So I'm glad of being here, and that's all. Thank you very much for your attention.
So we have now jury time. So questions, remember, not too long. 1, 2.
Okay, thanks. Can I see slide number 23, please? Yeah. As you can see, you have shown your comparison between data and your theory for the angle of 20 degrees, right?
Yes.
Where you have actually the best agreement.
Yes.
Can we see the other ones that are not that good, 10 and 15?
The other things that are here are the variation of the capsules, but we didn't include the variation of the angles. That are the other fits that we have.
Okay, but what would you expect? Would you expect that the theory still describes
Yes,
your
we
data?
think that there it's happened something very important because, as you can see, the angle there varies a lot. And what we see is that maybe when you has lowest angles, you have a combination of the two movements that cannot be like separated in our way. That first the sphere follow, after that the pill will roll in. We have a combination of both that in that cases, and for that reason the fit is not very well there.
Thank you.
From what I saw in your abacus simulation, you found something different or something extra from the theoretical model. So I have 2 questions regarding that. The first one is, what is the difference between the model considered by the abacus simulation and your theoretical model? Do you know it?
The first question is, the difference is when you change the dimensions, what simulation proof is that the movement is not only in one plane, it will change of plane. So we need to characterize that delay of time at the end of the total time. So our model, without that inclusion, will predict lowest final times than the real ones.
Yes, this part you said it before in your presentation, but what is the abacus simulation? What is in the abacus simulation model that is not present in your original model?
Well,
not the result, but like in the model consideration.
The consideration, for example, something that the opponent team says, there is considered the thickness of the pill, the material of the pill, the material of the sphere, that all are included there.
Yeah, as the opponent stated, he stated that there might be some losses of energy because of friction. So I'm wondering if your model is rolling without slipping in between the sphere and the pill, and between the pill and the inclined plane. So what do you think if you have taken an approach, an energetical approach? Do you still consider there is some losses of energy?
Well, what we can see here, we make the comparison of the energy before the heat and after the heat. And we notice that angular momentum has codified that losses of energy. The energy, when it starts to rotate, is lesser than when the sphere is going down. So using this formalism, you can include that losses of energy too.
So I have another question. You have a second linear equation for beta.
Yes.
Can you give me a little more information on how you solve this equation numerically, and
Yes.
if you have several solutions, and how do you choose?
We numerically we solve that equation with Runge-Kutta of our order. That was the step from, and the initial conditions were this one over here. How we can calculate the initial angular velocity. So we can use this initial condition into this numerical procedure, and obviously it starts from 0 and ends with p. That's the two conditions to solve numerically.
Okay. Apparently, in your finite element simulations, you use a radius of the sphere a little bit smaller of the cylinder.
Yes.
And also, we observed some movement in the transversal axis. Do you think this movement is related with the difference between the radius or
Yes,
not?
we think that is related
Why?
with that. Because if the sphere hits perfectly, the movement will be in this way. But if the sphere hits, for example, there, the movement, the contact point in which the angular momentum will be generated is this one over here. So it will flip in that axis.
But then you also simulate with almost the same radius, or
no,
not?
No, we
Why?
almost because it was very difficult to model that, because if the radius in the simulation that is considered the thickness of the pill is very similar to the sphere, there will no movement. So that was a difficult problem there.
Thank you.
One question. The assumption that the conservation of momentum depends on the interaction between the ball and the bottom of the capsule. I mean, you are assuming that the interaction is instantaneous.
Yes.
How will you improve your model in order to take into account that the interaction between the ball and the capsule takes some time?
Yes. That's a difficult question. I think I need to think about it, because we decide to use this because we think that other type of formalisms doesn't include the energy losses. But I need to think about how to include that.
Okay, thank you.
10 more seconds for any question? Yeah. Okay. The jury now has 1 minute to decide. So difficult. 1 minute. Okay, now it's time. So for the jury, again, let's start in a different order. Huh? So reporter first? Okay, reporter first. So yeah, the marks for the reporter then? That is 9, 9, 9, 9, 9. 8, 9, 10, 9, 9. Now for the opponent. The marks, please. Up. 866-4788-879. Okay, good. And now, for the reviewer, please, your marks up. 776-877-8778. Okay, good. Now Miguel is going to say something to you. Please listen to him.
Okay. Yeah, of course. So now it's the time for comments from the jury. Do any of you want to say something, ask something, put something on the table?
Thanks. I think that this problem is really nice, and it will be a beauty for the reporter to improve it with dynamical systems analysis, like phase spaces and some stability analysis. But it's pretty good.
Any other comment, suggestion, question?
We can congratulate people, right?
Yeah, of
or
course.
Not really?
Of
Okay,
course.
so I
Now-
would
now
like
it's the time.
to publicly congratulate the WIS team. It was really, really nice analysis and really good solution.
Woo!
That's a general overview of the WIS presentation and including all the participants. I think it's important to specify the system that we clarify right from the beginning if the momentum is conserved or not. I mean, this happened a lot with the jumping bean problem. For all the problems, I think there is a lack of a specification of what is the system, if it's the pill plus the sphere or just the sphere, and just a simple physics problem that begins with the specification of the system.
Thank you.
I want to congratulate. I think it was a nice presentation. However, if you consider that the radius of the sphere is a bit smaller than the one of the pill, it may hit the walls, but not also always at the end. Just take that into consideration, please.
Any other questions or comments?
I also wanted to congratulate you because I liked the presentation, and I think what I liked the best was the effort to give both a theoretical, experimental, and simulation approach, but also the fact that simulations corrected the theoretical model. I think some people just restrict themselves to like compare experiments with theory, but you also went a little bit after that and corrected your theoretical time with the delta t given by simulation, and I think that's interesting.
Nice. Now it's the time to comment and ask. Like there's no clock anymore because we're now introducing the grades into the system to see how things went out. So maybe now it's the time for the public to comment or ask something if they want. Federico from Universidad Nacional. Can anybody give him a microphone, please? Federico.
Okay, I just want to say something about Universidad del Valle, because last year they went to the tournament to Universidad Nacional, and well, they were led by Karen, and they did a very good job, and they didn't get it to the finals, and now this team that was last in the previous edition is in the finals of the tournament and did this incredible job, and I'm very surprised, and I want everybody to thank Universidad del Valle.
Definitely. Thank you for being here again and for such an awesome presentation during the whole 2 days. Is there anybody else who wants to say something, maybe clarify something about a physics problem that you just saw a discussion about or something? Maybe some of the participants or the groups. Juanes, could you please? Thank you.
About the simulation, did you take any data from the simulation, or it was just for the visualization of the movement?
Wait, could you please use the microphone?
Okay.
we extract for them the time delayed due to the changes of plane.
And in that case, did you make a convergence with the meshing of the capsule and the ball?
What? Sorry?
When you work in an FEA analysis, you have to do some meshing. Yes. My question is, did you make different meshings for the same simulation?
We try to make an even better meshing, but the reality is that the time that the simulation was running was too long, so we used this one.
And at the end, with the simulations that we made, did the results converge to something, or did you just make one simulation?
No. We made several simulations, as he showed, with the different meshing, and actually they convert with the
value, the delay of time that we include, it converts.
Okay, awesome. Maybe it's time to tell you something that ones of you might know, but maybe others don't, is that since there are a lot of juries, the rules specify that 25% of the scores don't get into account. And this translates into the fact that the average of the grades is calculated by taking away the two lower scores and one of the highest scores, right? So that's how the grades are being calculated right now, just in order for you to know that maybe sometimes creates, I don't know how to say this, like results that you don't expect, right? There's a question from Universidad Nacional. Can you give them the microphone?
Okay, I'm very happy to be here. Thank you. A lot of the Universidad de Antioquia because this event. And I just want to make a suggestion, and it's about the physicist. I am very happy that we again could be win or represent Colombia. And I think that is very important make a comparison between the experimental and the theoretical description of the problem. And I like that all of us could have the opportunity to make these experiments and see that the reality could describe with a theory, but is very different to make an experiment and have a really compare between the theory and the experiment. And thank you.
Awesome. I really feel what you just said. I've been something with the tournament for 3 years now. This is my third year in the tournament. The first one I was a student, a participant as you. Last year I was one of the leaders from the Universidad de Antioquia, and now I helped organizing this event, and I completely agree with what you say. Sometimes physicists and students stay at the classroom, at the paper, at the pencil, and forget what is actually to solve problems as the problems we solve here. And I think that's awesome. And yeah, I completely agree with that, and I appreciate that you say it. There's a question from Karen from Univalle. If one is maybe could give her the microphone. Sorry.
Thank you. I just want to congratulate all you guys for UPTC, for WIS, Univalle, Nacional, UDEA, Andes, everybody. I really enjoyed the tournament, and I guess all of you enjoyed the tournament. We, from Univalle, we enjoyed a lot the tournament, and we are really, really happy to be here. For us, it's as same as 1 year ago. For us, it was very, very difficult to be here without any support from our fellows back in Cali. But I really, after that, so that's the first thing. The second is I was a little bit worried about something I heard here. And the thing is we can build a Lagrangian for a dissipative system. So please do not be scared for dissipative systems. Actually, the real life has a lot of dissipation, and dissipation is lovely. We love, right? Dissipation. And you, of course, you. So Alonso is one of the guys that really work in kind of fields, and so we can build Hamiltonians and Lagrangians for dissipative systems, and it's a really lovely branch in physics. And the other thing that I really would like to point out, I guess it was not that clear as we would like to be in the presentation, is that for us, the ball rolls inside the capsule, and then which is much easier to visualize, is that once the ball is rolling, when it sticks to the capsule, then everything starts to roll, and then it's just one movement of everything, right? If this friction is not inside the capsule, then everything is not working well. And if you do so, then it's like you are moving a little bit when the capsule and the ball stick together, then just the center of mass shifts a little bit, and that's it, right? So this is something that improves a lot the model, right? So clap to everyone.
Woo!
Woo!
Okay, while our team keeps grading, which is a little bit of suspense, we want to invite you to tomorrow's event. So the event doesn't finish today, per se. The tournament finishes today, but the event doesn't. Tomorrow at 11:30 a.m., there's gonna be like a panel of a conversation between you guys, physicists of the tournament, and Juliana Restrepo, which is the director of contents in Parque Explora. Right now, we have two of them who are going to participate, which is Daniel Sucerquia from Universidad de Antioquia and Juan Manuel Pacheco from WIS. We would like right now to, even though Juliana is a physicist as well, we would like another woman to be in that panel for us to show the public that women also are physicists and are really good physicists, and we would like one of you girls to be in that panel. Is there any of you that might be tomorrow here that would like to participate in the panel? I know there's a lot of pressure, but we would really like that. Okay, I'm gonna keep that in mind. I'm just so there's one. Yeah, okay, another one from WIS. Woo! What's your name again? Laura Martinez is gonna be tomorrow as well. That's awesome. Thank you, Laura. Please tell your families. It's gonna be an interesting conversation between geeks, because I think I think that's how everybody calls us, and sometimes it's like an insult, but I think we all consider it a nice quality. I don't know if you guys, but I consider myself a geek and I love it. So I hope you also do, and make that conversation really nice to maybe motivate young people, young women to study physics or at least like sciences as physics engineering, as our jury told us during the whole weekend. I think that would be really nice. Okay, the other thing I would really like you to remember is that even though there's only one winner tonight, and there's only be one team representing Colombia, they're representing the whole country. So last year, it was really nice that when WIS won, I remember them reaching me. I don't know if they reached other people from other universities for for solutions they thought they were nice when we presented them. And I think that should happen again, because they're gonna represent all of us, and it would be really nice that all of us could help them do a better job that Weiss did last year. Weiss's job last year at the International Physicists Tournament was amazing. I mean, they got to the semifinals, which is our biggest achievement as a country in the IPT. So it would be really nice if whoever wins this time also achieves something similar or even better, if we could all help do that. I was gonna say something else. So I think team is strictly grading, so there's nothing to be left away and everything's fine. Right now, Alonso Otero, who is like the representative of Colombia for the for the International Physicists Tournament committee, yeah, is gonna say some words. He's been on this longer than any of us right now. Has been on this for 5 years. I think this is his 6th year, if I'm not wrong. He went with Los Andes a couple of times to the IPT. Then he made a national selection with Los Andes, Nacional de Bogotá, and UDA. When I participated 2 years ago, he kept helping, even though Nacional de Bogotá was the university who hosted last year's national selection. He kept participating, and today he's here. He's been the whole 2 days. He's been participating since 6 months ago, trying to make everything be as good as I think it has been. So, Alonso, please.
Gracias. Ok, voy a hablar en español para descansar un poquito. Bueno, entonces yo quería, primero que todo, agradecer a todos los participantes por el entusiasmo, por el trabajo tan increíble que hicieron pues, en la preparación de sus problemas. ¿Sí? Creo que esta ha sido la mejor selección nacional que hemos tenido, pues, digamos, pues, porque cada año pues, vamos creciendo, vamos aprendiendo, entonces esta curva es muy positiva, ¿cierto? Entonces, y todo ha sido una gran parte por el entusiasmo de los equipos. Tenemos este año un equipo adicional, o sea, ya estamos en 6 equipos. Queremos pues que esos números crezcan. Okay, entonces, muchísimas gracias a todos los equipos que participaron, primero que todo. Un aplauso muy merecido. Un aplauso muy grande también a todos los miembros del jurado que nos acompañaron en este fin de semana, que reconozco que pues, es una tarea que es pesada, ¿cierto? Ayer fueron 2 sesiones, como esta más o menos, y otra hoy, entonces pues es mucho tiempo, todo esto en calidad pues voluntaria por el entusiasmo con la física. Un trabajo fantástico, muchísimas gracias por su colaboración, y esperamos además que los jurados también pues, usen esta oportunidad como para entender un poco, pues, conocer el concurso y comunicar eso también a otras personas, a ver si entonces también nos ayudan a crecer la selección nacional para el año entrante. Entonces, muchísimas gracias. Ya bien, esa es la sorpresa del final. Sí, ahorita les digo dónde va a ser la próxima. Entonces, muchísimas gracias, miembros del jurado. Bueno, el otro lado de la ecuación, para que todo esto haya sido exitoso, pues es la parte de la organización logística que estuvo pues a cargo de un equipo de personas que estuvo trabajando todo el año en esto, logrando pues cuadrar los escenarios, cuadrar toda la parte logística pues de alojamiento, de pues, todo lo que tiene que ver con alimentaciones, toda la parte de, digamos, aquí hay mucho trabajo de tipo audiovisual, por ejemplo, que es importante tenerlo funcionando muy bien. Entonces, voy a leer los nombres, pues el comité local estuvo a cargo de Marco Giraldo y Miguel Vázquez. Esos fueron pues los... Y con un equipo conformado por Mariana Jaramillo, Valentina Bedoya, Samuel Hoyos, Sneider Vélez, Juan Esteban Aristizábal y Daniel Estrada, que no está aquí en este momento. Bueno, y una especie de miembro extraoficial del equipo que ha estado por acá rondando, lo han visto todos estos 2 días con la cámara, que es Jason Támara. Jason participó en la primera selección nacional que se hizo hace ya, pues, exacto, entonces es un veterano pues acá de la selección nacional. Perfecto, bien, de apoyo institucional también, pues tuvimos muy buen apoyo institucional este año. Primero que todo, la Universidad de Antioquia y la Fundación Universidad de Antioquia, pues por mucho apoyo pues económico, logístico también. Un agradecimiento muy especial al Parque Explora, ¿sí? Y en particular a una madrina que tenemos en el Parque Explora, que es Juliana Restrepo, que viene de la comunidad de los físicos, que pues entonces estuvo pues muy empática pues con el torneo. ¿Ah?
Y no sé, quiero esperar a que termines y yo digo algo más.
Ah, bueno, vale. Y bueno, y además a la alcaldía de Medellín también. Que nos ah, bueno.
Es que pensé que ibas a seguir con el Parque Explora. No, pues a Juliana claramente como directora de contenidos, muchísimas gracias. También tuvo muchísimo que ver, no nos pudo acompañar, pero tuvo muchísimo que ver Ana Ochoa, la directora de comunicaciones, digamos, encargándose de que todo esto fuera posible en cuanto a los espacios, a la logística, a los operadores. Por ejemplo, atrás tenemos también a Manuel en operaciones, y ayer nos acompañaron Sergio y Perea todo el día resolviendo absolutamente todos los chicharrones que se nos pasaban. Tenemos también a John Coronado atrás como jefe del CPA, junto con su equipo, trabajando el día de hoy, haciendo posible que sea la primera vez que se digamos, haga una producción audiovisual de este evento. Yo sé que el año pasado la Nacional hizo una mini producción muy bacana, filmando todo por Facebook Live también, pero digamos que todos estos equipos y todo esto es gracias también al trabajo de mucha gente, obviamente a las señoras del servicio y el aseo que estuvieron atentas con el café y con la comida y todo el tiempo. Sin todos ellos no hubiera sido posible. Acá tenemos a Margie Riaza, que es la comunicadora del parque, que ha estado publicando en redes las cosas que le hemos estado enviando, y hoy estuvo todo el día haciendo un cubrimiento del evento supremamente espectacular. Tal vez se me hagan falta decir algunas cosas, pero en serio esto fue demasiado bacano. Yo pues soy de la Universidad de Antioquia, pero en este momento soy trabajador del Parque Explora y me siento muy orgulloso de que esto hubiera podido suceder acá. Entonces quería agregar eso.
Aplauso muy grande. Bueno, también quería agradecer a otros miembros del comité del IPT para Colombia, bueno, y otras personas que nos ayudaron, por ejemplo, en particular a Federico Serrano. ¿Dónde está Federico Serrano? Se evadió. y José Daniel Muñoz, que también nos ayudó. José Daniel ya salió para Bogotá. Bueno, entonces, para hablar un poquito de la selección nacional, pues les comento pues, que esta es una cosa que ha ido creciendo pues, en los últimos años. Esta ya es la cuarta que estamos haciendo. La primera empezó entre la Universidad de los Andes y la Universidad Nacional. Pues les cuento un poquito cómo fue la evolución de todo esto. Unos estudiantes de los Andes hace 5 años encontraron en alguna página web por ahí, de ociosos en internet, encontraron pues que se estaba realizando este torneo internacional del IPT, ¿cierto? Entonces quisieron meterse, me dijeron a mí que si yo los podía acompañar, pues como team leader en esa época. Entonces esa vez fuimos al torneo en París. Y pues de ahí ya, digamos, los organizadores me encargaron entonces la tarea pues de tratar de crear pues este evento, que es lo que se llama la selección nacional, para entonces involucrar más universidades y de ahí sacar el equipo que va y representa a Colombia. Entonces eso se ha ido haciendo, yo digo que de una manera orgánica, o sea, invitando equipos y invitando jurados para que vayan y conozcan, y para que el año siguiente vayan entusiasmando a sus equipos. Y bueno, entonces esto ha ido creciendo. Esto ya es pues, entonces la cuarta, y hemos logrado ya 6 equipos. Entonces, como les decía, pues lo que queremos es que haya más equipos todavía. O sea que les dejo a ustedes también la misión de entusiasmar a otras universidades. ¿Okay? Ahora, a medida que va creciendo esto, pues va creciendo la complejidad de la organización. Con la complejidad obviamente crece también la magnitud de los recursos que se necesitan para que sea exitosa, y pues entonces ya se va requiriendo, digamos, más personal que esté involucrado. Nosotros el año pasado creamos un comité IPT Colombia, que en este momento está conformado por prácticamente pues al menos un miembro de todas las universidades que participaron hoy, salvo la UPTC, ¿cierto? Porque, bueno, que es el primer año que participan. Entonces, pues quisiera aprovechar esta oportunidad en particular para decirle a la gente de la UPTC que si hay alguna persona que estuviera interesada, por ejemplo, en hacer parte del comité nacional, pues que entonces que nos digan que estarían bienvenidos. Sería muy chévere contar con miembros de todas las universidades. Eso ayudaría muchísimo pues, en la coordinación, ¿cierto? Y bueno, y cualquier otra persona que quiera pertenecer al comité, también entonces están bienvenidos. Hay muchas cosas que podemos mejorar, digamos la consecución de recursos, de la parte logística también, la difusión del torneo, la parte pues de medios, etcétera. Entonces todo eso pues ya tiene que ser a partir de un comité. Entonces el que esté interesado pues que nos cuente. Bueno, y entonces pues ya no nos queda sino anunciar. No. Una última cosa antes de Mariana, que es entonces la próxima selección nacional, al final. Ah, bueno, listo, ok, entonces vamos, estos son expertos en el manejo del suspenso, entonces,
Buenas noches, nos hemos demorado mucho, pero ya por fin obtuvimos los resultados. Entonces, primero vamos a premiar los mejores roles, porque ya vieron que hay gente que tiene meras notas, entonces vamos a hacerle un reconocimiento pues en público por todo su desempeño en el torneo. Y ese reconocimiento se hace personalmente, es al estudiante por su buen rol durante todo el torneo. Si tuvo el mismo rol 2 veces, 3 veces, entonces promediamos esas notas. Por si se sorprenden con algún resultado, es porque hay un promedio detrás, ¿vale? Entonces vamos con los roles. Comencemos por el mejor moderador. el mejor moderador con un puntaje de 8.2 es Felipe Reyes Osorio. De Univalle, muy bien, excelente. Hiciste un muy buen papel de moderador. Creo que saliste 2 o 3 veces a hacerlo. Sí, seguro. Ah, bueno, te escuchamos hablar mucho. Estuvo muy bien, felicitaciones. Bueno, vamos a llamar a continuación al mejor opositor. Esta persona tiene un puntaje de 8.8 y fue Juan Manuel Pacheco de la UIS. Finalmente, tenemos una excelente nota para el rol de expositor. Es difícil obtener un puntaje tan alto. Y este puntaje corresponde a Laura Martínez de la UIS. Y reconocimiento a los tres porque desempeñarse en este torneo y en inglés es difícil. Entonces lo hicieron muy, muy bien. A continuación entonces vamos a dar los puntajes finales de la competencia. Falta una foto. Allá. Acérquense allá. Bueno, estos son los puntajes de la sesión de hoy. Recordemos que no contaba nada de lo que pasó ayer. Iniciamos con un puntaje de 41.7. Es un buen puntaje. Y este es para la universidad. La universidad. No estamos tan sincronizados como los equipos. La nacional. Felicitaciones. Bueno, solo resta descubrir estos dos nombres. Estos dos nombres. El ganador es la Universidad Industrial de Santander. Un aplauso para el equipo que también quedó en segundo lugar, la Universidad del Valle. Excelente. Excelente. Bueno, entonces vamos a pasar en orden o todos juntos. Todos juntos. Listo. Pasemos todos juntos. Adelante, adelante, para que tomen fotos, para que les demos los premios, para que se abracen.
Bueno, resulta que también de parte del Parque Explora hay unos premios para todos. Unos premios para todos los finalistas. Son los siguientes. Para todos los finalistas, una libreta del Parque Explora y el Planetario. Háganse más acá, háganse más acá. Las libretas son las mismas, pero tienen diferentes motivos. Si quieren, se las pueden intercambiar. Oh, ayuda. Sí, 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 sí. Para el tercer lugar, es decir, para la Universidad Nacional, unos mugs con motivos también del Planetario y del Parque Explora. Y los termos también. Esas dos para todos los segundos. Para Univalle, en el segundo lugar, tenemos unos cuadernos y unos termos también con motivos del planetario del Parque Explora. Son todos un poquito distintos. Ustedes se los reparten entre ustedes, ¿listo? Los que más les gusten no tiran la moneda o el dado. Y para los ganadores, unos morralazos. ¿Cómo se dice? ¿Cómo se dice morral en Santander? Mochila, morral, bolso, no sé, es que en todas partes se dice distinto, ¿no? En Medellín le decimos morral o bolso. Ahí sí ya depende de ustedes. Quédense por favor ahí para que tomemos ya la foto real, la foto oficial de los finalistas y de los ganadores. Ah, yo. Marco Alonso, hágale pe. Hey, Manuel, cae. Soy Dani, vení. Claro. Eso. ¿Listo?